Right. Good afternoon, everyone, and welcome to today's ARMETS event. My name is Daphne Sifignotti, and I'm a member of the events committee. Welcome all once more. A couple of things that I'm going to mention here for the ARMETS, and then I'll pass it to the rest of the speakers. One thing that might be of interest for you is the Met Matters is our enthusiast blogs. I'm not sure why this is changing. We're still here for all things that are relevant to weather and climate. If you'd like to sign up, just go on our site and you can sign up for the Met Matters. It also has opportunities to participate in citizen science projects. And you can hear from a variety of experts with guest blogs as well that are relevant, of course, to the energy industry as well as today. For the next one, if you are not a member of the Royal Meteorological Society, you can become one. Again, I'm not sure why this is changing. I'm not pressing it. So if you are interested in meteorology, you can join our society, and then the membership includes professionals, but also enthusiasts. So you can join. It has academic students, teachers, folks from industry or other sectors. You can have access then to the monthly weather magazine. You can have it online or even printed. And of course, it includes some discounts that you get if you're a member on conferences, journals, and access to support grants. So I would like to welcome the representative of EDF, Joe.
Yeah, thank you, Daphne. Nice to see so many people here today. So I'm Joe Eckington. I'm a research engineer in the Natural Hazards and Environment Research and Development team at EDF UK. So I just want to take a moment to introduce EDF's interest in space weather and why we think meetings like this are really important. So EDF is the UK's largest generator of zero carbon energy, and we operate a large fleet of nuclear power plants across the UK. And we're also investing heavily in the future of the UK nuclear industry as well, building a new power plant at Hinkley Point C and another one planned at Sizewell C as well over the next decade. And so ensuring that this nuclear fleet is resilient to different types of natural hazards is a really key priority. And of course, space weather is increasingly recognized as an important hazard for the UK energy sector. And so for many years now, EDF's been carrying out work into characterizing the space weather risk and understanding how it might impact nuclear infrastructure in the UK. And in particular, we're worried about phenomena like geomagnetically induced currents and ground level enhancements. But in order to understand how these can really affect the infrastructure, it's really important to work with industry, academic experts, and policymakers to better understand how to safeguard the infrastructure. And so we hope that meetings like this can be really useful in enabling that, sharing that domain-specific expertise, and also strengthening the existing links between different institutions as well. So hopefully everyone finds this event today really useful and takes something away that they find helpful. And very much look forward to hearing the presentations and panel discussion later. Thanks.
Good afternoon, everyone. My name is Nick Shaw. I'm the chair of the Board of Trustees of the Hazards Forum. We're delighted to be a partnering organisation for this event. In my day job, I'm a Principal Nuclear Safety Inspector for the Office for Nuclear Regulation. It's great to see some of my colleagues from ONR in the audience today, as well as some colleagues from our Hazards Forum's member organisations. I've been asked to say a few words about the Hazards Forum, so I thought I'd just delve into a little bit of our history of how we were founded. I thought it might provide some helpful context into who we are and why we exist. So the last 30 years of the 20th century were marked by several natural human-made disasters, which raised questions about the preparedness of national governments to prevent or mitigate the effects. For example, the Chernobyl nuclear disaster of 1986 was a serious and wide-ranging catastrophe rated 7 on the International Nuclear Event Scale, whose effects are still felt. It raised important questions about the way in which corporate management and government should respond to nuclear disaster. Similar concerns were raised by the 1980 Mount St. Helens volcano explosion in Washington State, which removed over 1,000 feet from its height and devastated a wide area. The Bhopal gas cloud disaster of 1984 killed 7,000 people and left the affected population without compensation or support. One of the largest magnetic storms of the last century occurred in 1989, which caused widespread effects on power systems, including a blackout of the Hydro-Quebec system. Here again, with all these events, issues of corporate responsibility and national governance arose. So these events, together with those nearer home, such as the Flixborough chemical plant disaster of 1974, the King's Cross Underground fire of 1987, and the Zeebrugge ferry disaster of 1987, all raise questions on issues of preparedness, assessment, mitigation, and governance. So against the same backdrop, the United Nations designated the period 1990 to 2000 as International Decade for National Disaster Reduction, called on member nations to form national committees for natural hazard reduction. So that this process began after Dr. Frank Press, who was president of the US Academy of Sciences, had called for such a decade in a speech to the American Earthquake Society in 1984. And it was in this context that the Hazards Forum was established. So if we go back to 1988, his presidential address to the Institution of Civil Engineers, it was Dr. Alistair Patterson who gave examples of several disasters and discussed the role of the engineer in hazard mitigation. And he commented, one element that each of these hazards has in common is the technology for the mitigation of their effect lies within the province of the engineer, who can hope to contribute directly to the reduction of consequences of these hazards. So on the United Nations call for the formation of national committees for natural hazard reduction, Dr. Patterson said that the Institution of Civil Engineers had taken the initiative in the formation of such a committee for the UK, and preliminary talks had already been held with interested parties. However, he had reservations about the prudence of this development, having regard to the overlap between natural and human-made hazards. He said that at this first meeting of the new body, it was intended to consider whether a hazards forum might be a better concept, giving consideration both to natural and human-made hazards. So following Dr. Patterson's lead, the Hazards Forum was formed in 1989 to encourage joined-up approaches to the mitigation of human-made and natural disasters and hazards. The founding partners were the Institution of Civil Engineers in association with the institutions of mechanical, electrical, and chemical engineers. And our membership has grown over the years to include members of regulatory bodies, the public and private sector, as well as a wider range of engineering bodies. So in 1996, the Hazards Forum became an unincorporated charitable association, and since then continued its path to fulfill its charitable object for the public benefit to mitigate and reduce hazards and disasters, both man-made or human-made and natural. So really delighted to be here. Thank you for your time, and I look forward to this afternoon's discussions.
Thank you to all of the representatives from our organisations that have helped organise this event. My name is Matt, and I'm going to be hosting today's event. So yeah, my work used to be at EDF, which is my connection to this event. So I used to have the role that Joe now sits in the natural hazards team at EDF Energy. I now work in the consulting firm called REA, which is an international consultancy firm doing work across Europe and Canada, across the space sector and in cybersecurity. So a bit of background and kind of motivation for this event. Space weather, as we all know, we're here. We know that it presents a hazard to the energy sector. It's been recognised for over a decade now by the UK government as one of the key civil emergencies. Amongst others are the risks from extreme pandemics, which we're now all too familiar with, unfortunately. The meeting is quite timely now as we're on the uptick towards the maximum of solar activity, which will be around 2025. This year already, we've had some quite large geomagnetic storms that have brought aurora down to Kent, I think I saw a picture from. Unfortunately, I moved down south to London. In the urban environment, it's difficult to see the Northern Lights, but yeah, maybe in the future. The previous solar cycle was unusually quiet. So much of the modern energy infrastructure that's been developed over the last 20 years or so perhaps hasn't had the testing from space weather effects that we think it that we think could be possible during this cycle and in the future. So there's a concern in the energy sector amongst other sectors that without this testing from moderate to extreme space weather events, is there a house of cards that's been built that could not be resilient to a major event that's towards a Carrington scale event? These are questions that that there's a community of research and an industry and government activities towards trying to answer. So it is a good time to bring the community together to discuss where we are with space weather resilience and what remains to be done. So it's a privilege to have 5 speakers today, which will cover all the way from academic research, industry, and government and agency activities. A quick overview of the speakers before we get going to whet the appetite. So we have Simon Machin from the Met Office, who is speaking about risks posed from space weather and the work of the Met Office Space Weather Operations Centre, the MOSWOC, to provide services to the industry to help monitor and forecast space weather. Then we'll hear from Matthew Houghton from the National Grid ESO about the effects of severe space weather on the electricity transmission system. Then we'll hear from Gemma Richardson from the British Geological Survey about the research into modelling geomagnetically induced currents in electricity grids. Then we'll hear from Alexei Glover from the European Space Agency, who will give a European perspective on space weather, and she'll be speaking about the European Space Agency's space weather service network, which I'm well aware has been improving year on year and working closely with the electricity and energy sector across Europe to provide services that are that can be used during and prior to a space weather event. And then finally, we'll be hearing from Mark Prowse from the UK Government Department for Energy Security and Net Zero, who will be speaking about the SWIMMER programme, which is a long acronym that will be defined in due course, which is UK funded research into space weather activities. Each talk will be about 20 minutes, and then we will have 5 minutes of questions for each of the speakers after each talk. We'll have questions from audience in person, but also we'll try and get some questions from online as well. People who are attending online will be able to type their questions into the chat, and we'll be able to ask those questions to the speakers. Following this, we'll have a 25 to 30-minute break, which will then lead us to the final session of today, which will be a panel discussion with the 5 speakers, which will last around about 45 minutes, which again will include questions from the audience here, but also from online. And we'll aim to finish around 5:30 today. Regarding fire and safety, there are no expected fire alarms today. So if you do hear one, the nearest exit is this one down the stairs, illuminated by the green light. And if anyone is in need of first aid, we have a few first aiders on hand, Catherine, who you probably met already, and Hayley, who was welcoming people at the front desk. Finally, during the break, we have a video, which I think has some sound as well, which will be on in the background as people are milling around in here and in the other room during the break. So without further ado, we'll welcome Simon for the first talk. He'll be talking about the Met Office's Space Weather Operations Centre, the space weather activities and support to the energy sector. Thanks, Simon.
Good afternoon, everyone. And thanks to Matt and everyone for inviting me and giving me the opportunity to be here and speak to you today. So those who don't know me, I'm Simon Machin. I manage the Space Weather Programme at the Met Office, which is the UK's national operational capability to support national resilience, to support critical industries in the face of space weather events. So first of all, just really to think about space weather and what space weather is very briefly. Space weather emanating from the sun. The Met Office have a bench at the MOSWOC, which is staffed 24/7, 365 days a year by space weather experts, monitoring the sun monitoring the activity on the sun, the active regions, to understand what's happening, what's developing. And what we're looking for are these sort of key categories of event. Things like solar flares, solar radiation storms, and geomagnetic storms, all driven by magnetic complexity and reconnection of the magnetic field on the sun, which can eruptively lead to eruptions in the sun, which can accelerate electromagnetic energy, particles, and lead to the casting off of huge areas, billions of tons of plasma. If these are Earth-directed and like to be Earth-effective, then, of course, these can have impacts on a whole range of systems. The solar flares are essentially electromagnetic radiation, traveling at the speed of light, of course. So we can't observe those and forecast their arrival, because by the time we've seen them, of course, they're already here. They're having an immediate effect. So when it comes to the forecasting side of the house, with solar flares, we have to forecast in a probabilistic way. We have to monitor the sun, monitor the active regions on the sun. And when I say active regions, we're mostly thinking about areas of sunspots, monitoring the complexity of those and the magnetic field around those, and coming up with a probabilistic forecast of flares of certain magnitude over the next few days. With solar radiation storms, it's not totally dissimilar. Again, these can travel at very close to relativistic speeds, be it sun to earth in a matter of minutes, perhaps more often in an hour or two, but again, traveling very quickly. Not something we can observe lifting off the sun, but something we can sense in spacecraft, particularly the spacecraft at the Lagrange 1 point, which gives us just a few minutes, maybe a few hours notice of arrival at Earth. So again, there's very little we can do in the deterministic forecasting space, but we can do probabilistic forecasting based upon those active regions again. And when we get readings from the spacecraft at Lagrange 1, about 1 million miles from the Earth on the Sun-Earth line, then of course we can issue warnings, although relatively short notice warnings, and then alerts when they actually arrive. And then the geomagnetic storms, which are vast areas of plasma, they carry with them their own magnetic field embedded in that. And depending on the characteristics of that, if they're Earth-directed, they can lead to geomagnetic storms. If the magnetic field contained within that has a strong negative or southward component, then it's likely to be more Earth effective. If it's a northward component, much less so. It's going to be deflected around the Earth, much like poled bar magnets would do. The geomagnetic storms are arguably the most important of those, in that they can lead to long-lasting storms and generate the GICs, the geomagnetically induced currents, that are most important to the electricity industry. So, but space weather can impact on a whole range of systems. So here, I won't read out and go through all of these, but let's say a huge range of communications, as well as energy reliant systems, things like GNSS that can be impacted by space weather. Perhaps the most interesting ones and the most relevant ones to the energy industry, of course, are things like the induced currents in long conductors generated by the ground induced currents, which can potentially lead to power grid failures. Also upsets to ground-based electronics. These can come about as a result of what we call ground level enhancements, when we get particularly energetic radiation storms that, through something we call an atmospheric cascade, lead to penetration of neutrons down to ground level. This can be many magnitudes of increase and lead to upsets to ground-based components, which can be, of course, important to ground-based command and control. Also, of course, communications, some of these other things, communications, GNSS, particularly for timing and synchronization, can be important. So there are some other things on that list, again, that we need to be cognizant and aware of when we're considering the holistic risk to electricity. Matt already mentioned this in his preamble there, but the last solar cycle, looking back at the solar cycles and the maximum of activity here, going back to the 1950s, the last solar cycle was particularly low, lower than all of the most recent cycles. and anomalously low. Not only anomalously low in absolute extent, but anomalously low in the fact that we didn't experience any large geomagnetic storms within that cycle. That's really quite a rare thing. I'll put the next element on here. Here I've got mapped solar cycles going back to 1934. And marked on there, I've got maximum and minimum periods within each solar cycle. The blue bars representing KP9 storms, or if you like, geomagnetic G5 storms. This is the top of the scale, geomagnetic storm, and these are the ones that we think are likely to be impactful to the UK national grid. So what's of note here? I think there are two real big takeaways from this. One is those blue bars don't coincide with solar maximum necessarily. That's a key takeaway. Whilst the solar maximum, we will see more sunspots on the sun, we will see more solar activity, more space weather events, doesn't necessarily mean we see the very largest events. They can be, and are possibly got a slight tendency to be more prevalent during the declining phase of the cycle. If we're looking at the years, the next few years, we're probably looking at 2025 onward. The other big takeaway here is that the last of those blue bars was back there in 2005. We've had no KP9 G5 storms since then. So exactly as Matt said, the systems that we've been building over the last 15 to 20 years haven't been tested in the face of a major geomagnetic storm. Clearly, some components may be tested in radiation environments, some components may be hardened, but we don't have a clear picture of what that looks like across the UK grid and control systems. So I think there's some key questions and some things that we would do well to find out around that. Of course, historically, there have been large space weather events. Looking further back, the likes of the Carrington event, which I assume most people will have heard of, in 1859, the largest recorded event of modern times. However, there have been significant events in 1921, 1989, where famously 6 million people lost power in Canada for 9 hours. So events do happen, impacts are experienced, and even as recently as 2017, a much smaller scale event resulted in some electricity transformers tripping out in Scandinavia. I think one thing that's really worth considering is also the global threat that space weather poses. As opposed to traditional meteorology, hurricanes, large-scale storms might affect 1, 2, or 3 countries, perhaps part of a continent. Space weather, when we experience the big events, they're going to be global events. 2003 was one of the last large events that we saw. And here, if we're going to thinking about electricity, well, there were impacts and damage on electricity grids as far apart as Scandinavia and South Africa. So we clearly need to think about the global picture, global interconnections. And if we're considering the risks associated with damage that might occur as a result of a big space weather event, we need to be thinking about global supply chains. I think that's been ably demonstrated over recent times with some of the issues that have been experienced post-COVID. Space weather has been on the National Risk Register since 2011 as a fairly high risk, not as high as pandemic flu. The latest iteration from 2020 is perhaps slightly less visually appealing than that earlier version. But space weather, one of the more significant risks. And I've got 2023 on the top there because we're expecting the new updated National Risk Register to be published any time now. It hasn't been published yet, so I'm not going to say any more about that. But I expect that will be published in the next month or two. Underpinning that, we have a reasonable worst case scenario, and the risk assessment that underpins the National Risk Register describes severe space weather as an event that's likely to be in the order of 2 weeks, well, more than an event, a series of events with individual phenomena consisting of those flares, radiation storms, coronal mass ejections, and many of those within that 2-week period. They will vary in magnitude and extent across that 2-week period, but clearly there are likely to be impacts across a whole range of systems, which could be simultaneous, could be rather unpredictable, as will the space weather phenomena in themselves. And there lies one of our key challenges. Back in 2013, the Royal Academy of Engineering published a document on extreme space weather and the impact of the UK. At that time, the assessment was that around 13 transformers could be damaged on the UK national grid as a result of extreme space weather of Carrington scale. Again, things have changed since 2013. That was obviously a decade ago. Things evolve, and so it's high time that some further assessment work were done to update that risk assessment. In the Met Office, as I mentioned, we have the Met Office Space Weather Operations Centre. We have an expert there sitting on the desk 24/7, 365 days a year, monitoring the sun, pushing out alerts, warnings, forecasts, and providing advice, providing reach-back advice to National Grid ESO control room as and when they need that, and to other users as well. One of very few operational centres across the globe, about 5 at the moment, UK, US, a couple in the US, South Africa, Japan. So we're quite a small club, although space weather is growing. Many countries are developing their own space weather capabilities, and we're talking to and supporting many of those in the development of those space weather operational centres. At the MOSWOC, we support both public government as well as critical national infrastructure and our defence community. We have access to a range of information. British Geological Survey magnetometers, for example, which give us near real-time data, which we can monitor the impacts of space weather, monitor the impact of coronal mass ejections, and use these as the basis for a warning service, warnings and alert service, as well as using them for ingestion into models. And one of those models that we use is the Enlil model, which models the solar wind, but also the coronal mass ejections that get cast off from the sun. And as I say, these are the things that lead to the geomagnetic storms. These are probably the most interesting and most important aspect of space weather. So we run this model, input the CMEs, and provide forecasts based upon that. But not just deterministic forecasts, we run ensembles of this model to try and quantify the level of doubt, the probabilities around coronal mass ejection arrivals and geomagnetic storms. And that's what this plot here is showing, some of the scale and scope of probability around those CME arrival forecasts. We provide a range of forecasts, written forecasts that describe the situation, together with those probabilistic forecasts I mentioned, geomagnetic storms, solar flares and radiation storms, going 4 days ahead. We produce 2 flavors of this one. We produce what we call a plain language version that can be generally used and understood by the non-expert, whilst we also produce a technical version that's really aimed at people who understand space weather terminology and can apply that in their day-to-day operations. We also produce forecasts of geomagnetic activity through the KGBI scale there, forecasts out 24 hours ahead on this case, and we actually produce another one that goes 3 days ahead into the future. And as I mentioned, a whole range of alerts and warnings, which people can find through our website. You can sign up to receive as many or as few alerts and warnings as you wish. The Swimmer program is really important in developing our capabilities. What we provide now is the best we can, given the capability that we have, given the data and information that we have. But it's clear there are some gaps in that, not only with forecasting the effects of geomagnetic storms, but across the board with space weather. And back in 2019, we were fortunate enough, well, put together a case with a group of colleagues that went in and became funded through UKRI, through something known as the Strategic Priorities Fund. And it's going to be enhancing our forecasting capability, our modelling capability through the working with partners across UK academia and the research councils to develop and onboard new and additional and enhanced modelling capability at the Met Office across all of these areas. We're also going to be and are deploying new instruments to measure space weather effects. Spacecraft, we launched spacecraft a couple of weeks ago up into low Earth orbit. That will be raising to about 645 kilometers and providing us with measurements of radiation from that environment. We're also going to be flying monitors on aircraft and installing ground-based neutron monitors in the UK. Expecting to install two, one in Lerwick in Shetland, the other in Camborne in Cornwall. Should be really useful in monitoring those ground level enhancements and provide us with a new capability, one that we have not had in the UK since the 1980s. This radiation testing facility called CHIP-IR at Harwell, again, SWIM will be enhancing that capability or has enhanced that capability. Here, there's an opportunity for people to take components in and test them in a realistic space weather environment. There's an opportunity here, perhaps, to introduce and develop new standards, and perhaps that could be useful across the electricity and other industries. And finally, I mentioned the 2013 space weather study. Well, Matt and colleagues at RIA are leading on a piece of work to deliver an updated space weather impact study as part of SWIMMER. And again, I think that will be an incredibly valuable piece of work. As regards the electricity industry, some of the key ones are alongside the obvious ones, if you like, the electric field modelling, the sun to earth modelling that will tell us more about CMEs and geomagnetically induced currents. Also projects to enhance ionospheric modelling, important for communications. Taking those radiation measurements, important for monitoring and alerting. And also, as I mentioned previously, that facility to test electronic components. Clearly, the electricity grid has changed and is changing. Renewables are changing the whole picture of generation to distributed generation, away from monolithic power generation in a few locations. Exactly what that means for resilience, I think, is at the moment still a little bit of an open question, but there's some work that will be done on that. And I think, again, that will be incredibly useful in helping us to better understand. And then from our side, of course, to use the information we can to inform operating procedures in the electricity industry. We also have the Severe Space Weather Preparedness Strategy, published in 2021 by Bayes, as it was at that time, and Mark and his team behind this, really. 3 pillars to space weather preparedness: assess, prepare, respond and recover. Assess is clearly the space that the MOSWOC and the Met Office work in, assessing that risk, developing forecasting capabilities that align to user requirements, and then tailoring what we can do to actually meet the operating requirements so that people can make real decisions, people can make proper decisions that can help mitigate against the impacts of space weather. And I think that's one of the key things. And one of the things we're doing a great deal of now, really under the auspices of the strategy, there's a work plan that sits under that, with key sectors, obviously electricity being one of those. We're doing a lot of close work with the electricity, but with other sectors as well, to try and help assess the situation. Where are the vulnerabilities? Where are the gaps in knowledge? Where do we need to do some more research? How does that need to be targeted? And so, I say we're doing some great, really interesting work in that space at the moment, and getting some great results back from industry as regards those interactions, which is really absolutely fundamental to get into grips with space weather. And as I say, tailoring what we can do to meet those user requirements. So on that, I'm going to wrap up for now. And so thank you very much for your attention. I'm really happy to take questions if anyone's got any questions, and obviously be part of the panel session later on.
Thank you, very interesting. Can I ask a question about your predictions, the way you predict space weather events?
Yeah.
What is the sort of accuracy, or can you come up with that space weather predictions? And the second part is, how good are you at predicting extreme events?
Okay.
Events. And no, it's a very difficult question to answer, but how far along the road are you on this?
Okay. Accuracy wise, well, we do actually monitor our warnings and provide feedback actually to our own in-government department, and which is DCIT and DESNES, the Department for Energy Security and Net Zero. So we report back to them on accuracy. By and large, accuracy is a problem with space weather, because one of the big issues we face, and particularly with geomagnetic storms, is that we don't really know with much certainty what the absolute magnitude of impact or scale of event is going to be until we get those measurements at L1. For a fast-moving CME, a coronal mass ejection, that might mean as little as 20 minutes or half an hour's notice. So we produce watches days ahead, but the actual warnings and forecasts, deterministic forecasts we can produce are much shorter scale. So we're actually quite good at our short-term forecasts, but what people really want is the longer-term forecasts, which to a great degree are beyond our capabilities at the moment. What people really want to know is at 24 hours notice, am I going to get a G5? And our skill score at that at the moment is very poor. We're not on our own. That's the state of the science at the moment. There's a lot of work being done on that, of course, across the academic community, some really interesting work. But we had some visitors from Austria a couple of weeks ago, came to visit us at the Met Office and demonstrating some of their modelling work, some quite interesting, innovative work that they've been doing. So accuracy at the sort of timescales that the user community really want the forecasts at the moment is very poor. Short-term forecasting wise, it can be very good. And clearly we want to try and bridge that gap through some of the work that's, and things like the swimmer program will help us to do that. I hope that's sort of answered the question on accuracy. Sorry, what was the other part was? And the extreme events, yes. Well, of course, we haven't experienced a big extreme event for quite a few years. The Met Office Space Weather Operations Centre has been operational since 2014. So we haven't had a really large, in fact, the largest space weather event we've had in that period was about a month or a couple of months ago. So we haven't had a really large space weather event during that period. So we can't really judge ourselves, to be quite honest. We have procedures in place, and we have a plan for that day when we see a really big complex area of sunspots that we think will have the potential to generate the next Carrington event. We've got products and specific briefing products that we produce for government and critical national infrastructure to give people as much of a heads up as we possibly could. But there is a risk that we could be caught out. And I wouldn't deny that. But as I say, and this is one of the reasons we have a centre at the Met Office, because we've got eyes on the sun throughout the day, throughout 24 hours. We're monitoring what's going on. And if things start to change quickly, if things start to develop very quickly, we're as confident as we can be that we'll be on the ball, that we'll be raising flags, we'll be contacting people like Mark and getting him out of bed at 2 o'clock in the morning, perhaps, and saying, there's something here we need to be concerned about, and we'll play it through that way. So I think we would be well placed, given our capability, given the people we have involved here, to actually raise the flags at an appropriate time and to alert people to the probability. But the deterministic forecast is always going to be difficult. I hope that's sort of helpful.
Thanks, Simon. I think in the interest of time, we're going to have to move on to take any more questions from that session.
Yeah.
Thank you, Simon. Great. Next, we have a talk from Matthew Houghton, who works at the National Grid ESO. He'll be talking about the effects of severe space weather on the electricity transmission system. Thank you.
All right, afternoon, everybody. My name's Matt Houghton. My job title is National Planning Manager at the ESO. So my main job is to plan the network and the power flows on the network and hand over that to the control room where I work over in Wokingham. So I'm going to talk about the effects of space weather on the grid. So I'm going to start talking a bit about how the solar weather can affect the power system and how that can lead to risks in terms of system operation. Some of those risk factors and the mitigations that we put in place and plan to put in place at the ESO. Okay, so this slide really sort of highlighting the areas of solar weather that we would be concerned about from a ESO's point of view, and how that leads to risks on the transmission system. So beginning from the left, we've got coronal mass ejection, which is obviously the solar phenomena that leads to geomagnetic storms event at Earth, that leading to the effect of geomagnetically induced currents in the Earth and in the transmission system, and then to saturation of transformers on our network. So that's probably where the biggest risk we feel that the network has to solar space weather. Also there we've got ionospheric storms, which could affect navigational satellites and the timing signal that is produced by those satellites that some systems could be dependent on, but I'll get to that later. And then we've also got radiation storms causing single event effects on Earth, and that's either actual physical damage to transistor gates, for example, or effects in digital logic where it could, sorry, skipping forward by itself, I think, or causing, some sort of digital or logical effects that might affect memory in systems, or basically have cause digital systems to maloperate. Okay, so moving on to focusing now on the geomagnetically induced currents. So from these currents, you can have secondary effects that are produced basically by the fact that the transformers are saturated. The magnetic flux within the transformer can be saturated. That can cause transformers to heat up. Certain parts of the transformer will get hot, and in severe cases cause damage and possibly destruction of that transformer. We can have increased absorption of reactive power. I'll get onto that in a minute, but what the result is effectively a voltage drop on the transmission system. And we can also have harmonics in the power, the current and voltages on the network, essentially noise within the power system. So if I just start now with talk a minute about the transformer flux saturation. So this curve is meant to explain how the GIC causes our transformers to be excitation current to increase. So on the left hand side, we've got a graph showing on the y-axis we've got the magnetic flux within the transformer, and on the x-axis we've got our current, and the flux density shown by the nice little sine wave there, and how that transfers into the excitation current. And excitation current just is a small part of the current within a transformer, and it's just the current required to set up that magnetic field within a transformer. So the GIC, which is a direct current, would push the magnetic flux into the non-linear part of that curve. So you can see on the right-hand side, we've got a saturated transformer where the magnetic flux is above the normal design parameters or the capability of that transformer as core, and going into the non-linear region over the knee point. That causes you to have a very large excitation current, which you can see on the bottom of the graph there, a big spike. So that results in two effects. One is the fact that the steel core of the transformer, which is shown in the grey, is a steel core of the transformer, is now saturated, and the magnetic fields are basically leaking out of the transformer, shown by the little dotted lines. So this is a simplification of a actually on the system we would have quite a lot of three-phase transformers, also single phase in certain areas, but the magnetic field is leaking out of the core and inducing stray flux magnetic fields within the different parts of the transformer where they wouldn't normally be. So in the tank walls of the transformer, in the flux shield, and particularly important in the core bolts and clamps that basically holding the bits of the transformer together. So that stray magnetic flux causes currents to circulate within those bits of metal in the transformer, essentially. That might mean that we see transformers disconnecting because condition monitoring systems detect heating in that transformer. Although, because it's quite localized, it might be just a bolt within the transformer is heating up. It might take a while for that heat to come through to the sensors and trip it off. So it could lead to permanent damage to insulation within the transformer, and that's what's basically happened to that transformer at the bottom there, that picture, which is from 1989 in North America. Different transformers have different vulnerabilities. Single phase transformers tend to be most vulnerable, followed by three-phase, what's called five-leg transformers. Basically, each leg of these, see the grey columns is basically a leg of a transformer. And you can also have three-phase, three-legged transformers, which are most resilient, but still can be affected, can be damaged. Okay, so we talked about the flux and the heating effects. That's where our heating can come from and possible damage. Now we're talking about the absorption of reactive power, which is another secondary effect from your GIC. So first of all, what is reactive power? Well, so a simple way to think about it is the reactive power is required on an AC power system to set up electric fields and magnetic fields so that the real power that actually does the work can be transmitted across the network. So from its generator to the demand. Without those magnetic and electric fields, it just doesn't happen. So you need some reactive power. And so you can think of this in a very common analogy is the pint of beer. So our real power is the actual beer itself, and the reactive power is the foam or the head of the beer on top. You can't have one without the other if you want a proper pint of beer. And on the power system, it's a matter of balance between having the right amount of reactive power to make sure that real power is transmitted efficiently. So on the power system, we have sources of reactive power, and we have sinks of reactive power to create that balance. And that's what that picture on the right-hand side there is showing a picture of an SVC, which is static VAR compensation. And the VAR is just what reactive power is measured in, the units of reactive power, and the compensation, meaning it's compensating for the balance, making sure there's a right balance of reactive power on the network. So back to our chart earlier of the transformer showing the large excitation current component. And that excitation current, as I explained, was to set up the magnetic field within the transformer. So this transformer is driven into half cycle saturation, absorbs more reactive power than normal. The large excitation current lags behind the voltage by 90 degrees. So that's just the phase angle of the currents versus the voltage. And that creates a reactive demand in that transformer. reactive demand increases linear with the GIC current. So more GIC you've got from space weather effects, the higher this excitation current is going to be. Reactive power, as I said, is used to for voltage support and to balance the reactive power and make sure we have the right volts across the network. So during a storm, you're going to see high GIC levels of high GIC. You're going to see a large excitation current in certain transformers, and that will cause a voltage drop at those locations on the network. And hopefully it will work. There we go. Okay, and the third effect. So I've gone through two: the heating, the voltage drop. Oh, we've got a slide problem. Third effect is harmonics on the network. Sorry about this. I think it's, oh, there we go. So back to the curve within the transformer, because we're now operating outside the linear portion of the transformer's capability, into the non-linear portion of the saturation curve. A large excitation current drawn by the transformer, so the current required for that magnetic field contains harmonics. In other words, it's a noisy signal. So that noise gets added on to the load current across the network, represented by the little wiggly lines in that chart there. So that has a potential to cause damage to capacitors, filter banks due to harmonic heating. It also got the potential, there's a potential risk to HVDC equipment, interconnectors, due to the fact that they use filters and power electronics to convert the AC into a DC. There's also a risk of protection relays maloperating. So a protection relay, we have protection across the whole network, and what it does is switch out equipment or assets from service if they detect a fault. So you don't want that circuit for safety reasons, and also for the fact that you don't want to damage the equipment any more than you might have already done. So it'll remove it from service. The risk here is that harmonics could trigger protection relays when you don't want them to trigger. And there's, the risks can be combined. So you could have a loss of reactive compensation equipment like that SVC I showed in the picture on the last slide, which is there to balance the reactive power, make sure we've got the right voltage levels. You might lose that due to protection malfunction, but then you also have an increase in reactive power absorption from your transformers at the same time. And that's actually what they think happened in Quebec in 1989. So they were seeing voltage drops at the same time they lost reactive equipment. Other possible impacts mentioned at the start, that satellite navigation timing signals, the satellites themselves could be affected by an ionospheric storm. For us at the ESO, we not consider that as a significant risk because we do use backup we have backup. We use it, but only as a backup to internal timing sources. We do have a small amount of protection equipment still relies on this signal, but it does have virtually all, I think all actually assets have secondary or redundancy there, so that they have backup protection that is not reliant on, in this case, is not reliant on that timing signal. And there is work ongoing to remove that dependency. And then finally, radiation storm can causing single event effects. I think this is probably one of the areas is less well understood. And obviously that can affect any digital system, not just on the power system. And understanding how, what the risk is to certain equipment and what that might mean to system operation probably needs a bit more work on that. Next one is just looking at the reasonable worst case scenario. So shown here in the orange, the G scale, or the geomagnetic storm severity scale, provided by the Met Office. So the level we're concerned about as the ESO is really the G5 scale. Sorry, a G5 storm, which average frequency is 4 days per cycle. But of course, within that G5, we've got the reasonable worst case scenario, which is the 1 in 100-year event, or Carrington-like storm, which we would expect to see very high reactive power demands. So that's causing the voltage to drop, as I explained. Likelihood of thermal damage to 10 to 20 transformers. And that's a statistical value. If we were to lose transformers, it doesn't necessarily mean we'd lose demand, but I'll come on to that in a minute. In a 1 in 30-year event, would be classed as a major storm, a likelihood of voltage disturbance and transformer alarms, and 1 per cycle. We just see voltage disturbances on the network, 2 to 3, maybe some minor disturbance and small fluctuations, and in some cases might not actually see any effects. So it's quite a large range, obviously, within that G5 storm severity. Okay, so risk factors. What impact? What increases or decreases risk across the network? So geographic location is important in terms of GIC. The further north you go, and geological structure affects the GIC we would expect to see. There's also coastal effects, and edge of the transmission system tend to see higher levels of GIC on the coast and at the edge of the system. Longer lines, so the longer the line, the higher the voltage or stronger the electric fields are going to be. I mean, in this country, relatively short lines compared to maybe some other countries. And high voltage, again, our highest voltage is 400 kV, which is shown in the blue, and red is the 275 kV. In Canada, for example, they go up to 735, and China 750 in some parts of their networks. Transformer design obviously has a big impact. As I said earlier, some transformers are more prone to GIC effects or heating effects than others. And we have looked at transformers across the country to monitor, to assess the risk of individual transformers. So risk levels and possible effects. So we think having a major disruption to electricity network with a recovery time of years is not really a realistic scenario. We think there's effectively zero chance of that when we're talking about GIC and our reasonable worst case scenario of a 1 in 100-year event. In a 100-year event, we'd expect to see damage to a small number of high voltage transformers. That could possibly lead to 1 or 2 nodes on the network disconnected. But we would have, if that were to happen, then we think there are spares available that we would be able to mobilize and get those nodes back on service relatively quickly. Reactive power demands. So 1 in 30-year event, we could see widespread voltage disturbances across the network, and in 1 in 50-year event, possibly local power outages. But again, there wouldn't be any permanent damage. It would be a matter of returning those demand points in maybe a matter of minutes or maybe a bit longer than that. Okay. Mitigations. So we receive warnings and notifications from MOSWOC and from BGS. For the 3 sort of categories, we've got transformer damage, and these are the kind of mitigations we'd put in place for that to reduce the risk of those events or the impact of those events. Essentially, try to get more assets back into service. so that if we're all constantly taking outages on the network for maintenance construction work, and we, following notifications from MOSWOC and BGS, we would look to try and return assets to service where we could, to try and increase the resilience of the demand of those areas, and depending on where, you know, locationally where the outages were, if they were a higher risk area or not. We cancel start planned outages, and also I didn't mention, but you know, generator transformers are also potentially at risk. So repositioning interconnectors to maximize the flexibility of those interconnectors so that we could access additional reserves of generation if we needed to. Reactive absorption and voltage depression. So again, we'd look at the levels of reactive demand across the country, and we do this as a kind of day-to-day thing anyway, but we'd review that to make sure we've got the right levels of reactive capability on the network in terms of the generation, because they can also supply it, but also in terms of equipment like SVCs or capacitors and reactors, and whether there's anything we can do to maybe get some of that back in service. And then harmonics, so previous investigations have been completed that showed that the protection on the system was resilient to harmonic effects, and we don't think that is a major risk to the network in terms of tripping out circuits. Okay, and finally, just to round off the presentation, just a couple of thoughts on the future requirements. So, as was mentioned earlier, the network has changed significantly since the 2013 Royal Academy Engineering Report, and will change a lot more between now and 2030. We have ambitions for net zero. We're looking to connect 50 gigawatts of offshore wind by 2030 and consider an extra 25 gigawatts, considering we only have 28 at the moment. That's a big change. We will require 54 billion pounds worth of network investment on the transmission system, and the image there is just showing the reinforcements that are required both onshore and offshore to achieve that. Obviously going to be new technologies on the system. It's going to be a much more flexible network in terms of balancing supply and demand, new carbon capture generation technology, potentially new nuclear, long duration storage, hydrogen production and generation, more interconnectors, mass EV charging. There's going to be a lot of change and potentially a lot of control systems that could be at risk. So the work is ongoing to look at this and review those risks. So that's the end of my talk. Happy to take any questions if we've got any time.
Thanks, Matthew. I think we'll just take one quick question. Perhaps we'll take it from the online audience.
It's exactly the same for Simon, so we can keep it for the panel.
Okay, yeah, no problem. Give me one quick one.
Thanks, Eben Tenley, Met Office. Our current forecast to you kind of predicated on the idea of once you've seen a CME lift off, so that's kind of a 3-day maximum advance warning. If you had what you'd like, what sort of lead time would you want to be able to mitigate effectively?
Ideally.
Yeah, in the ideal world.
Yeah, so ideally would like at least 24 hours notice of a G5 storm, and I think Simon mentioned earlier that's quite difficult to make that prediction, but I think there's probably a balance in terms of how often you send your forecasts, which might be for a G3, G4 or higher, I think, versus us taking actions and overreacting and taking actions that do actually reduce the risk. So I think we have to that as part of our process is to look at the different actions we can take and which ones we can take, given the notice that you can already provide, and the ones that we might have to take later on when we know, right, we actually, a storm has started, we don't know how long this is going to last, but you can still take those mitigation actions even if it's already arrived.
And could you would a lower accuracy, lower skill, but longer lead time forecast, probabilistic forecast be actionable at all for you or not?
For some actions, yes, and some actions we wouldn't be able to take, I think, because there'd be too much uncertainty and we wouldn't want to be doing that frequently. There's also actions that we're working with the industry and the DNOs and generators. We're in discussions at the moment about how we communicate those actions to them and where depending on what level of forecast you provided, which ones we would ask them to take or not. All right.
Okay, thank you. Up next, we have a talk from Gemma Richardson from the British Geological Survey, who'll be talking about understanding geomagnetically induced currents in the Great British Power Network. Thanks, Gemma.
So, hello everyone. This kind of follows on quite nicely from Matt's talk. This is a bit more of the kind of science behind GIC and how we model it and what we can do. So I thought I'd better start with a bit of an introduction because I wasn't quite sure who would be in the room, but I know a lot of this has been covered already. So space weather really is just a term to describe the conditions in space that might affect us here at the Earth. And this is the kind of classic plot, which I'm kind of surprised hasn't already appeared today, showing you all the kind of range of different impacts that space weather can have. And in terms of what I'm going to talk about, I'm going to focus on this bottom bit, but it is important, as we've already heard, to kind of remember that context, that it's not just one effect that's happening at the time of a severe space weather event. In terms of GIC, again, as we've already heard, for those big, severe space weather events that are going to cause GIC, it starts with the coronal mass ejection, which is this big kind of cloud of stuff that gets ejected from the solar corona and contains solar magnetic field, which when it then arrives, bumps into the Earth's magnetosphere. And we've already heard it called a geomagnetic storm, but again, I just thought I'd kind of explain a little bit about why we call it that. So this plot up here at the moment is what we measure on a typically quiet day in terms of magnetic field. So the top line is the declination, so that's just the angle from north of the magnetic field. And then we have the horizontal intensity in the middle and vertical intensity at the bottom. So the background numbers of those are quite large. You probably can't quite read them. But for the horizontal intensity, for example, that's 17,500 nanoteslas. But most of that is coming from the core, the magnetic field that's produced in the core, and some of it's crustal, but they're kind of very static in terms of the kind of timescales that we're interested in for GIC. But the external sources, so things happening in the ionosphere and the magnetosphere, are these kind of faster variations. So in a quiet day, we have this daily variation, which is this quite smooth curve. During a geomagnetic storm, we can no longer see that smooth curve because we've now got much larger ranges of activity and it's varying much, much faster. So that's why we call it a geomagnetic storm. And again, as we've already heard, that causes our GIC because we have varying electrical currents in the ionosphere caused during this geomagnetic storm, which then induces a magnetic field in a perpendicular direction, which in turn induces an electric field in the ground, which then means that there's currents flowing in the ground. And particularly if you've got very resistive rock, those GIC find their way into nice low resistance infrastructure like power grids, and they can cause kind of disruptions to your AC operations, as we've already heard from Matt. I'm not going into that. Again, I had just a few examples of GIC impacts. We've already heard about 1989 and 2003 a few times, but I'd also mention 2001, which was a probably less intense storm, but for the New Zealand grid, it hit at perfectly the right time for their side of the world, that it actually caused a fairly significant storm in New Zealand and damaged
the transformer at Halfway Bush, which was subsequently found to be beyond repair and had to be replaced. So it's just another example that we've not heard yet of, you know, damage that can happen even from not necessarily the biggest storms, but that one in particular was all about the timing. Okay, so that's the background. How do we actually model GIC in the grid to be able to give people at National Grid an idea of how to mitigate the effects? So firstly, we need to know what the magnetic field is doing. So we need to know all those variations in the magnetic field. And we need to know something about the conductivity structure of the ground, because those two things together can then give you the electric field. And then if you add a power network model in, you can get the GIC. So just to kind of work through those in a little bit more detail, here's a particularly good example of us having lots and lots of measurements of a geomagnetic storm. So this is the September 2017 storm. I will say we don't normally have this many measurements. This was a bit of a fluke because we had a school's magnetometer project going at the time. So we had lots of extra magnetometers measuring. And these, the traces on the right, on the left there are ordered from the highest latitudes at the top down to the lowest latitudes at the bottom. So for this particular storm, you can see at high latitudes, again, as we've already heard mentioned, they experienced the most significant variations during the storm. And then we can take those kind of measurements, interpolate them with a system. In this case, we've used the spherical elementary current system method to get an interpolation of magnetic field all across the UK. And X is just the northwards direction and Y is the eastwards direction. Okay, so in terms of our conductivity model, what we do at the moment is we have a conductivity structure of the UK based on the map of bedrock geology. And that gives us the conductance in the top 3 layers, top 300 kilometers, no, top 3 kilometers. We'll get there in the end. At the surface, so that tells us about a kind of shallow-ish conductivity structure. And then beneath that, we have these, I think it's 6 or 7 terrains based on lower level geology. And each of those is just a simple 1D model with depth. And then what we can do is we can iteratively solve. So you've taken that magnetic field, you iteratively solve from the bottom up to the surface, and then the surface electric fields are redistributed by what we call our thin sheet, so that conductivity structure at the top. And that gives you an electric field. So as you can see, this is the electric field from that same storm, and it's strongest over Scotland, as you would expect from those plots of magnetic field. But that's not the only way to get the electric field. You might wonder why we don't just measure it. We have all these magnetic measurements. Well, we do actually measure electric field, but it's very, very difficult to measure. And it's very, very difficult to keep it kind of baseline stabilized and all those things that we can do very easily with the magnetic field. So it's not high quality, and you wouldn't want to trust a model built on those real-time measurements. So the other thing you can do is modeling. So I've explained the thin sheet modeling. In an ideal world, you'd have what you call a 3D inversion to get the full 3D structure of conductivity. But that is firstly very computationally expensive, and secondly needs lots and lots of measurements, which in the past we've just not had. And actually the thin sheet model gives us a pretty good answer for a lot less computational effort, which means we can use it operationally. But what we're working towards now is a measurement campaign measuring what's called the MT, so the magnetotelluric measurements, which is just measuring the magnetic and electric field at the same time, at the same place, for all these sites in red. This is what we've done over the last couple of years. And once you have those, you can calculate what's called the impedance transfer function. And if you have the transfer function, and then you have magnetic field observations, even once you've taken away your MT site, you can go directly from magnetic field to electric field and then interpolate that across the country. So again, it's very computationally inexpensive once you've got that initial transfer function set up. So that's what we're working towards. That will hopefully be an improvement as we go along. So once we've got our electric field, we need our power network model. So the way we do this at the moment is we take information from the 10-year statements from National Grid, and we dig out the line resistances and transformer resistances and all the connections between all the substations. And then we make a few other assumptions around things like grounding resistance and the few other kind of bits of information that we need to give us our power network model so we can work out where those currents are going to flow. So once we've got all that and put it all together, we can then actually model the GIC. So this is, again, that example for the September 2017 storm, which, as we've already heard, was a G4 event. So that means the KP, which is the global measure activity, reached KP 8. And then on the right-hand side here, you can see the GIC. So each of those circles represents the GIC through a substation. Now, that does not mean that because one's red or yellow, that substation is going to, have major issues, because this is the total current through a substation. So there might be lots of transformers, and the current would be distributed through all the different transformers, and it depends on transformer type, as we've already heard, is what's there. But what it does do is it gives a kind of idea of which parts of the grid are being most affected at any one time. So for this particular snapshot of the 2017 storm, just like the electric field map I showed you before, it's the high latitudes that we're getting more impacted. If we have a look at the 2003 storm, which is now a much bigger event, you can see it wasn't just that it reached a G5 or KP9, it lasted longer. There were kind of these two big phases as well. So it was quite a big event. Again, not the biggest we've measured, but quite a big event. And you can see in this case that we've got more of these kind of larger circles. So there's more substations that are experiencing higher GSE according to our model. And not only that, but we're now at a much lower level, because during the really big geomagnetic storms, the area that's affected expands equatorwards, as well as just getting stronger. So more areas get affected. Okay, so that's kind of the UK picture at the moment. These models that I'm showing here are from our kind of real-time system that we've built as part of the Swimmer project that we've heard mentioned a few times. But we've also been working on some kind of other things. And so just to place this in a wider context, as we've heard, these kind of events are likely to be global, and they're certainly likely to be regions, like quite large regions, all being affected in a very similar way. So we're part of a project called Euphoria, which was looking at the interconnected European grid. So we've been looking at, when the UK is being affected, the rest of Europe's also being affected. And then the other project we've been looking at is this Solar Tsunamis project. And it's a project based in New Zealand, but New Zealand is actually very, very relevant to the UK, because in geomagnetic terms, it's at the same latitude as the UK. So you can draw a lot of parallels between the kind of size of events they see and what we'd see in the UK. And the really interesting thing about New Zealand grid is Transpower have made available lots of GIC data from the grid. So actual measurements of actual GIC going through transformers. So all of those stars there are places that they have been measuring GIC for some amount of time. You'll notice the halfway bush near Dunedin is in red. That was one of the places that got GICs put in after that transformer failed. So it really kind of kickstarted their interest from a space weather perspective. They actually originally had the measurements because of their they have a huge HVDC connection which has return currents through the earth. They need to understand where those currents are going. But what that means is, like Daniel's done in his paper, you can go away and actually compare what our model says with what the measurements say. And in this particular example, you can see the blue is the measured data, the red is the model. And you can see we're doing a pretty good job. One of the things that we have found is we tend to generally underestimate the size of GIC in the network. So we're having to do some kind of different things to try and account for that and understand why. Now, the other really interesting thing about the Solar Tsunamis project is that we've got, from a scientist's point of view, we've had a much bigger insight into how mitigation work is being done. So one of the things Transpower have done is they actually commissioned a report to define threat levels within different transformers. So this has now been published and it's an open access paper, so it's out there for us all to see. And it shows you, so in this table, basically you have the mean current you would need for the amount of time you would need to get a transformer to 180 degrees. So you can see as the size of GIC increases, the time that you need to have that GIC for reduces. And that means you can do plots. So the plot on the bottom there is Daniel running some different simulations of different storms using different kind of input assumptions and seeing which transformers in the grid would meet any of these threat levels. Now, I should point out that a threat level of 5 isn't necessarily worse than a threat level of 1. It's just you need a lot less time to get to that level. But what you will notice is the single phase transformers at the bottom require a lot less current. It was already mentioned that single phase are more at risk, but I have been assured that there are no single phase in England and Wales, at least, in the transmission network. As for Scotland, I don't know. I haven't found the right person to ask. But they've also been doing lots of work testing their mitigation strategies. So Daniel, who's been doing all this work, went and actually sat in Transpower's operations room with his model, and they ran through a whole load of scenarios saying, well, if we took that transformer out, or if we took that line out, what happens? And that is work that I think he's going to publish quite soon. So that'll be really interesting to see the results of that kind of real collaboration between the science and the operations. And then the last thing they did, which I am quite certain we would never get permission to do in the UK, is they actually pumped a whole load of current into one of their substations to see what happened. There were obviously lots of controls, and the people in the control room were very kind of wary about what was happening, and lots of things were monitored, but we took lots of measurements while we were doing that. So we were measuring GIC in the lines, the BAS were there with measurements of the harmonics, and obviously Transpower themselves had the GIC measurements. So again, hopefully within the next few months, some of that work will start to get published and get out there, but unfortunately I don't have any results to show you today. So I thought I'd kind of finish with some areas where I think there's some gaps in, certainly in our understanding, and ideas where things we can work on in the future. So as I've mentioned, we do make some assumptions about the network, so it would be great if we could actually get a bit more kind of accurate information, but obviously there are difficulties around kind of confidentiality and things like that, which I understand. And then the other thing is, again, we've heard this mentioned a few times of our Carrington type event, or our 1 in 100-year storm. And one of my issues with that is we don't actually know what the Carrington event did. We know it was really big. We know that there were auroras seen down south, you know, way past London, and even with the lights of the city, people could still see the northern lights. But here is an example of one of our magnetograms from the Carrington event. And this is taken at Greenwich, and you can see it's not entirely easy to disentangle the different lines. This is quite a good example. One of our other observatories, the line actually goes completely off the page. So we know the minimum maximum size, but we don't know how big it actually was. And you can see where the kind of really tight squiggles are. Basically, that's where it got higher frequency. But again, we can't see how fast it was changing. We can't see the size of the different variations. And the equipment that was being used at the time has much more lag in it than any equipment that we have now. So we can use it as a kind of approximation of what a storm might look like, but it's not necessarily obvious actually how to model that and how to say this is what an extreme event would look like. But we can do things with 1 in 100-year kind of statistics, so we can scale previous storms and assume things scale linearly. But I think there is still some debate about how we actually model this. And then there's another question about whether we should move to higher frequency magnetic field measurements. So most of our work up to now has been using 1 minute magnetic field data, but actually we now measure to 1 second. And there is some argument that if you use 1 second data to model your GRC, you actually get much larger peaks. And it's whether those large peaks are important because they're very short-lived. But maybe we need to start looking at whether we get those kind of higher frequency, higher peaks fed into our models to understand how a storm might behave. And of course, we need to validate our model. You know, I showed those plots before, and we have done some validation of our model. We have some of our own, what we call DMM measurements, where we've measured GIC under the line. We have some measurements from a few sites in Scotland. I think we could do a lot more to actually properly validate our model and give confidence that our model is actually giving us the right answer. And then the other kind of thing that I was thinking about, again, our model is very, very static. We say that's the answer for that grid. But as Matt's already mentioned, the grid isn't static, it's changing all the time. So one thing we could look at is, are there certain lines or certain connections or certain transformers that are more important in terms of GIC distribution than others, that would be the key ones to get back in if they were out of service in the event of a space failure event. And just more work on GIC mitigation procedures and learning from other people, particularly like the work that's going on in New Zealand at the moment. I think I'll just leave the summary there for you to read and take any questions. Okay.
Take a quick question from the room, and then hopefully we'll have time for one online as well.
Do you know if, so I'm Andrew Larkins from Sygensis. Do you know if there's any regular direct monitoring of GICs within the GB grid that could be used to help validate your model?
I have recently discovered that there probably are a lot more measurements than we've ever had access to. At the moment, we have a kind of ad hoc agreement with Scottish Power that if I remember to ask them close enough to a storm happening, they can send me some measurements. But I've recently discovered that actually in the national grid transmission side, across England and Wales, they have been installing monitors since 2012 or 2013. So there are lots of measurements, but it's getting access to them that is the tricky bit.
Okay, thank you.
Let's try and take one from online. No? Okay, maybe another quick one from the room.
You talked about currents in the transformers, but surely and timescales for which the transformers are potentially damaged. But surely that depends on the rating of the transformer. If I've got a transformer with 10,000 amps capability, then 1,000 amps is going to be far less of a problem than if it's 1,000 amps capability. So how does that? I mean, I think there's obviously some more work that needs to be done there.
Yeah, I mean, that's based on, so the numbers that I gave before are based on Transpower's kind of standard 3-phase unit and single phase unit. I'm not sure what their ratings are.
Yeah, there's a big range. Obviously,
Yeah.
they're a relatively sparse grid in New Zealand compared to this country.
Yeah. But it's kind of the first time they've really put numbers on it that are so openly accessible that we can, you know, actually run it through our model and say, okay, that transformer might be experiencing that amount of current for that amount of time. So.
Yeah, sorry, I might be more, but I just basically a per unit figure would probably be a more useful one for people. So
okay.
Percentage of the transformer capability.
Yeah, I can ask that question, whether it's possible to get some kind of per unit or percentage type thing back, but it's not my area of expertise, I have to admit.
We've got that one more.
Thanks very much. Obviously, there's a lot of talk about overhead power lines. I was just wondering if there's a read across to all the overhead cables on the railway, all the electrification and network rail at all, and how what the impact is there.
Yeah, it's a question we're starting to think about a lot more. I think the actual power system for the rail is at a lower voltage and therefore not as susceptible, but yeah, I think they do have some quite long lines at the same time. So it's something we would like to look at least, even if it's just to reassure ourselves that it's not a problem. But again, it's getting the right contacts to get into the right place and the right funding to do that. But we would like to.
There has been some recent work published this year, I think, from the University of Lancaster Group.
Yeah, so Cameron Patterson.
Research on the GIC effects on track circuit.
Yeah, that was specifically looking at track circuit and signalling issues. We are trying to get some funding for us to work with Lancaster and look at a wider range of impacts. But.
Yeah, it seems like very little model you think about that, but what they flag up seems somewhat aligned. Okay, I think that's it.
All right.
Thank you. Okay, thank you, Gemma. The next talk is from Alexei Glover, who I think has travelled the furthest for the talk today. So thank you very much for that. She comes from the European Space Agency and will be discussing ESA's space weather service system in support of the energy sector. Thanks, Alexei.
Thanks very much, Matt, and thanks to the organisers for the invitation to speak here today and this very interesting and diverse session. So I'm going to give a short introduction to ESA's space weather service system and some of the work we're doing together with the energy sector representatives. For a bit of context, I'm working in ESA's Space Weather Office, part of ESA's Space Safety Programme. And within the space safety program, we address hazards from space and their impacts on our society and our technologies, developing systems and solutions to help mitigate those effects. And so within space weather, we are developing a space weather service system geared towards addressing space weather impacts from the sun through to geomagnetic conditions and the potential impact on our technologies. The service network that we're working with at the moment, we are what we call pre-operational. So we are the services themselves are accessible, and you can reach them via our website. It's free to register, and if you haven't already done so, I would invite you to do so. And the services are available continuously, but supported during normal working hours only. So we take very seriously the timeliness and the reliability of the information, and so these are typically available with an overall 95% availability. So the services themselves, as we've introduced earlier on in the session, to look at space weather, we're looking at conditions from the sun all the way through interplanetary space to the magnetosphere down to the ground. And to address this and to put together these services, it's made possible by a network of more than 50 different institutes, industry and academic groups, grouped into 5 what we call expert service centers, addressing that domain from solar weather through to geomagnetic conditions, really bringing in and building on really a wealth of European expertise and capabilities. So we have 29 services, including a service addressing the energy sector, but addressing domains from space-based operators through to ground-based operators. And they're built up on a network of more than 260 individual products and tools. That number will grow in the summer. We are preparing right now a big release of new and upgraded capabilities. So this will continue to develop. But who uses these services? We have more than 3,000 registered end users from many different sectors, from commercial industry, from the academic community, from government organizations and representatives also. We see around, on average, more than 2 million hits on the service portal monthly. That varies with different conditions, of course, not least given the amount of space weather activity ongoing at the time, but also if we're organizing training events or also taking part in an upgrade. Okay, so how do we build the space weather services? And this slide is intended to be very, very busy. As I mentioned, there's a lot of different components and a lot of different expertise and resources that go into building the services. But we also recognize we're working with different users with very different backgrounds from different sectors and end users, and also beginners and also experts. And so we don't expect the users to be able to search through a big list of 300 products to find immediately what we need. So together with that network, with the expert service centers, we structure this information into end user services. So combining those products that are most relevant for a particular impact, a particular use case, a particular sector, working also together with the impacted users. and together with them build the service that best meets their needs that we're aware of. So our process looks a little bit like this, starting always from the customer requirements. We're developing services and we want to always to meet the needs that the users give us. Then looking at what products, what information do we have available to us? What can we do? Which of these needs can we meet already? Carry out a gap analysis. Are there areas that we're not able to address yet? In that case, then embark on development, integrate the results of the development through a service construction phase, and then go back to the users to see how we're doing, to see how much closer we're getting to the information that they're looking for. So what do we provide for the energy sector at the moment? So if you go to the service portal, you will see something that looks a bit like this. If you're logged in and you go to the power system operation service domain, which you can see navigate to via the left-hand menu, you will see at first step our dashboard, which is intended to give a snapshot of some of the information that our users have told us is important for them to see at a first view. So here you can see it's grouped, the information is grouped according to notifications in this column, current conditions, so information about what we see happening at the moment based on near real-time data and measurements, and forecast tools that are modeling and looking to predict what upcoming conditions will be. Then following the dashboard, you can also then click through for more information to the full service, and that will take you through to a further page with more user guidance, tailoring information about how to use the individual components, and also to reach out for more information to the first and second line support structure if you wish to do so. And what's important, just to come back to briefly, this is an extract from our customer requirements document, which was a large consultation with end users that we carried out at the beginning of the Space Situational Awareness Programme a few years ago now, but it forms the basis and has formed the basis over the past years of the service development activities that we've been carried out, updated and further informed as time has evolved and user needs has evolved with interaction with the end users. And we are right now just about to roll out an update of this document with the coming portal release in July. So again, that is the website. So if you'd like more information, please do register. So a few more words about working with end users. And this for us is really an essential part of our research to operations process, and also equally an operations to research process as well. And in that, the feedback from the users feeds directly back through that continuous improvement process into the development work that we're doing. And so we interact with the user community in a variety of ways. And as I arrived, a few people mentioned a webinar that my team had been organizing earlier this year, which they participated in as an introduction to this domain and how to navigate through exactly this information on the portal. But it is something that we address on many levels through outreach events, through training, such as the webinars. When we carry out a development project, we always ask the teams to engage with representative end users to get their feedback in their initial concepts as part of the initial definition work. And then once the once the implementation work is close to completion, then to go back to the end users to see how well we're doing and what adjustments we might make and what we might also think about that we've learned from this project to take forward to another one. Just a bit of advertising for campaigns coming up. I mentioned that there's a major release coming up in July. So we'll be carrying out user test campaigns around that release over the summer. So additional participants are always welcome. So we're always looking for people to test the products and give us feedback. We also do a series of tailored service campaigns and bulletins for high priority users. We are right now preparing one for the energy sector, which will start off later this year. You can see a snapshot on the screen there of a dashboard that's being put together specifically for this campaign to rapidly prototype together with the users involved the type of information that they would like to see. This is a multi tabbed dashboard. This is just what you see here is the summary, and then the next tabs go into more detail about GIC and geomagnetic conditions. And this is something that we've done regularly with multiple sectors, and find it a really useful way to engage, to understand how people are receiving the current information, also to understand more about the delivery and how people would really like to receive this. If a website is most appropriate, a tailored bulletin on a regular or threshold-based delivery scheme, or even an SMS-based service for alerting is the most appropriate way to receive information. So it's a very active program of developments. So what kind of information are we providing? So these are some example products that you can find if you delve a little bit deeper into the power system operators service. You can see top left, we have a map provided by the Finnish Meteorological Institute, estimating or nowcast GIC conditions in a representative grid. It's not the current grid, it's, I believe, from the 1970s, but it's intended to show the feasibility of the approach. And to give a representative indication of how active conditions are at the time. We have products giving a rate of change of magnetic fields, EV by dt, from Institute of Space Physics on the bottom left, and the top right's the Danish Technical University, based on the magnetometer stations they're operating in Greenland and the Danish mainland, and also different indices calculated by using different techniques and models. Some examples from BGS, who are providing a number of products via the portal at the moment, and also in the opposite end of Europe, in the south, the University of Alcala, also providing a GIC index based on work they have done with a regional operator in Spain. So to say a few words about ongoing and upcoming developments, I've mentioned that there's a large release coming up, which we're very excited about. So it's one of the largest releases that we've ever done as a network, with more than 60 different products and product upgrades coming in July. We're also revamping our service pages a little bit, giving them a fresh look and feel, taking on board some of the feedback we've received from the users over the recent periods. I also highlight one product in particular, but it's certainly not the only one targeting this domain, again, coming from our colleagues at BGS. In addition, we also have related development projects running in parallel. One relevant for this area is a development activity currently being carried out by University of Bergen and Imperial College, to explore the use of 3D magnetospheric modeling, global geospace modeling in service provision for this domain in particular. So they are currently demonstrating and testing two global geospace models, Space Weather Modeling Framework and the Imperial College Gorgon model, if you're familiar with them, to test and demonstrate their ability to provide product outputs, including ground magnetic perturbations and geomagnetic indices, nowcast and short-term forecast at this stage based on input solar wind data. Also expected to start this later this year is a related but different type of activity that we also focus on, which is an end user application interface. So this is a software development activity, which is really geared towards developing a customizable user interface, allowing end users to access and work with the content on the portal and tailor it to their needs, potentially run models behind and really exploit the results, building on that wealth of information and those individual products and data that we see available via the network. So that's currently in planning, and we anticipate we'll be moving forward with that later this year. Then looking at the longer term view, so we talked about the need for longer term forecasts and how our skill score at the moment is not what we would like it to be, whereas our users would ideally like a very accurate several day forecast of conditions likely to trigger major GICs. So to work towards addressing this, we're also looking we're further developing end-to-end modeling capability particularly through the Virtual Space Weather Modeling Center, which you may be familiar with. This is a capability that is also in an initial version available and reachable via the service portal, and it brings together and couples models from the solar corona through the heliosphere through to geospace. So this is also developing in the longer term view is to ultimately be able to combine and couple these different elements together to be able to increasingly provide advanced notifications for end users. Then I'll say a few words also about our space segments and ground-based measurement development activities. Space weather services, of course, rely on reliable data sources, and we know as a community that certainly there is a lack of data, and which we aim to build on and to address. So one of the key areas that's the program is targeting is to develop the concept of a distributed space weather sensor system. I think in this talk, I don't have time to go into all the different elements that go into constituting the D3S. And we were fortunate that we grew a lot at the last ministerial council. So I'll just touch on a few elements that are, I think, relevant for this talk in particular. But you can see some of the elements on the right-hand side there. For hosted payloads, we're currently flying radiation monitors, onboard magnetometer. We're developing small sats and also many other elements. And also, this doesn't exclude also ground-based measurements. So one project which we're also very happy to have recently completed was the MAG Sweden activity. Through this and the collaboration, which ran as a collaboration between the Geological Survey of Sweden and Danish Technical University, we were able to deploy 10 new magnetometer stations in Sweden, Greenland and Denmark, and also upgrade an existing 4 to a 1 second sampling rate. So able to capture some of the very rapid fluctuations that are often associated with enhanced possibilities of GIC. So these stations are all now up and running. Then the data is feeding in real time into the products that you can access via the portal, and also available for scientific use and exploitation for further analysis. Then a few words about the Aurora mission. This is the smallsat mission, which was approved at the last ESA Ministerial Council meeting at the end of last year. So the primary objective of this mission is to work towards 24/7 observation of the Aurora Borealis, to monitor the interaction of the solar wind and CMEs with the Earth's magnetosphere and Earth environment, helping to identify, monitor and nowcast the effects of geomagnetic storms and substorms, leading to improved services across many sectors, including this one. We anticipate help improve our magnetospheric and ionospheric modeling for space weather nowcasting and forecasting. And we are throughout this period going to be working closely with the scientific community to help to further refine the use cases and the algorithms and the techniques that we will deploy to be able to get the most out of this mission. Some preliminary characteristics of the mission: it's anticipated to launch into a circular 7,000 kilometer polar orbit. The main payload, which drives the mission, is going to be the imagers. The wide field auroral imager, consisting of an optical spectral imager and a UV imager in addition, also complemented by a radiation monitor and a magnetometer. The implementation's in 2 stages. We're right now developing the single satellite Aurora D, the demonstrator mission, which is currently anticipated that it will launch in 2027. And finally, a few words about the visual mission to L5. This is a flagship mission, really a cornerstone of the space safety program, and key developments ongoing. This mission is really targeting to provide unique monitoring data from the L5 vantage points. So it will allow us to continuously observe the sun and the heliosphere from that off-sun Earthline perspective. Enabling observation of active regions several days before they potentially rotate into an Earth-facing position, allowing us to monitor their evolution for longer periods of time prior to eruption. How it will, in combination with measurements from L1, enable more accurate characterization of CME, coronal mass ejections, as they take place closer to the sun, and also help us monitor the propagation and evolution of those phenomena as they propagate towards the Earth, with those two vantage points, and it helping us resolve some of the current ambiguities that we have inherent in our forecasts. And what's important as well is that the data availability is aimed to be in near real time, so it's really a mission designed to support operational applications. And will complement the current L1 baseline that we work with, and it will be made up of a combination of remote sensing and in situ measurements as well, which will also help us to characterize features in the solar wind as they rotate towards the Earth several days in advance. So we really anticipate that this mission, due to launch in 2029, is really going to enable a step change in our forecasting capabilities and help improve substantially on our accuracy. And I think with that, I will leave it there. That's all I had.
We'll start with a question from online.
Yeah. How robust are satellites at the moment for a big solar storm? Are we likely to lose GPS?
A very, very specific question. I mean, all satellites, most satellites are designed to withstand the environment that they're launched into, and including a representative worst case for that environment. And I think GPS is no exception to that. I think when I think that the challenge indeed is in characterizing what can be. We talked a little bit about a reasonable worst case earlier on in the session, and I think our environment standards do define this based on the observations and measurements that we've seen so far in recent the space era, when we've been making space-based observations. The question is to what extent that we may see events that are stronger. But,
Hi, Alexi. Just a quick question on your on the dashboards that you're providing to users. So they're quite technical, and it was just wondering, obviously you've got this fantastic loop of customer needs and going back afterwards. We've found that at Met Office with various sectors, so like the satellite sector, deeply geeky engineers, they're very happy with highly technical graphs and things.
Mm-hmm.
And I could imagine that the power sector could be like that, but I'm not certain. And it was just wondering what what the feedback has been in terms of are you giving them what they want, or do they need simpler representations?
Thanks. That's a really good question. And I think again, it's a mixture. In fact, as we see in most domains, we quite often have some engineers that are really very knowledgeable, want an API to the data, want to retrieve the data and use their own tools to process it. Others are really coming at space weather as a new subject and would like something very visual, simplified, and to be notified if there's something happening that they should be aware of, and then would like an expert to be on call to support them. So I think it's a bit of a mixture, and those dashboards give us a really good sort of reference point to be able to talk people through those sorts of scenarios. And I think the application development that we have upcoming later this year is going to be a really good opportunity to address exactly that sort of question. We have actually, with another development which we're rolling out as part of the release this summer, developed a multi-layer group of products effectively. So depending on the expertise, the interests of the user, they can stop at the first layer, which is a summary, or click through to increasingly more technical information.
I'll leave it there.
Thanks.
Thank you again, Alexi. Great. So up next, we have our final talk before the break. So speaking is Mark Prowse from the Department for Energy Security and Net Zero, who will be telling us about their developments of our understanding of severe space weather and its potential impacts on the UK. Thanks, Mark.
Thanks, Matt, and thanks everyone for having me. It's really great to see a broad spectrum of people in the audience. I'm always slightly wary about talking to a pure space weather community about space weather because it will become readily apparent most of the audience know more than I do. But also, I don't need to convince core space weather experts of the importance of looking at this risk. And so being able to talk to a wider audience is a really positive thing for me. So I'm Mark Prowse. I am a Deputy Director for the UK Government. My expertise and experience is in high impact risk planning, and particularly in relation to risks that will impact the energy sector. I'm also the Government Senior Responsible Owner, which is a catchy title, for severe space weather. So I oversee the severe space weather strategy and its implementation across all critical sectors the government is responsible for. So as shown here, over the last 20 years, UK investment in civil space has had a significant impact on the economic prosperity of the UK and space sector productivity. Our strong heritage in space has allowed us to support wider UK GDP by more than 300 billion in 2018 figures. That's probably taken a slight hit over the last few months, but it's still a good figure to be using. Key industries such as telecommunications, navigation, Earth observation, and meteorology have all benefited from this investment. Space is now identified as a strategic sector, which underpins many of the essential services our public are relying on for their daily lives. The increasing dependency on ground-based services that infrastructure has in space means that we need to do more to ensure that the mitigations to manage the risks posed by the space environment are factored in, and space weather is a key part of this. Reflecting the widespread and significant nature of the impacts, and to demonstrate the UK commitment to being prepared should the risk manifest, we've identified a senior responsible owner, currently myself, but we've also published our latest strategy, the UK Space Weather Preparedness Strategy, which sits underneath the UK Space Strategy. The strategy sets out how we will build our resilience to severe space weather, ensuring science and technology are integral to our understanding and the mitigations we develop. It therefore directly supports the aims of the refreshed 2023 integrated review, as well as the 2021 National Space Strategy, through greater integration of science and technology into policymaking. The strategy sets out our 5-year vision for boosting UK resilience through a series of commitments, and I'll take you through those shortly. I'm acutely aware that a severe space weather event will have global impacts, as the people who have spoken before me have shown. Therefore, a key objective of the strategy is that we enhance international cooperation over the next 5 years. And finally, the strategy will ensure that our understanding and mitigations that we put in place keep pace with the advancements in technology as we move forward. And I think Matt put it well, the energy system of 2013 is no longer reflective of the current energy system. The energy system of 2030 will look very different again. So having said international stakeholders are really important, here's a list of just domestic stakeholders. So this probably needs a bit updating, but what hopefully this shows, it brings together key stakeholders in the science community, the policymaking community, and the practitioner community. And I think this is really important. And as I said, a bit tongue-in-cheek at the beginning, there's no good scientists talking to themselves, policymakers talking to themselves. We have to take the new developments in science, the improved forecasting that Met Office and other partners are providing, the technologies that ESA and others are doing, bring those to policy makers so we can set our appetite for risk and where the public will have to pay ultimately, and then get that information to the practitioners, ESO in this case, but across all critical sectors to be able to take in actions. So severe space weather, as this diagram hopefully shows, covers multiple departments in government, multiple public sector bodies. The Department for Energy Security and Net Zero is the risk owning department, in our language, the lead government department for the risk, and we're heavily supported by our colleagues in the Met Office. We are responsible for coordinating the cross-government work programme to ensure that appropriate preparedness and mitigation measures are in place for those critical sectors that are going to be most affected, aiming to minimise the impacts from space weather where possible and respond to them as quickly as we can. On the capabilities side, the UK Space Agency works to deliver the UK's civil space programme, a key factor in our strategic direction. UKSA are also responsible for engaging with owners and operators of the UK space-based capabilities to ensure their equipment is resilient to severe space weather. And as we see new people enter that market, new technologies, new capabilities, we need to rethink our engagement with that community to ensure those new entrants understand the implications of space weather. Mentioned by Sai earlier, the Met Office Space Weather Operations Centre provides what we think is a world-leading space weather forecasting service, 24 hours a day, 7 days a week, and acts as a central hazard manager for the risk. Sai will certainly not be the first person who's woken me up at 2 in the morning saying there's going to be a big problem. And then experts. Some of you are here today, but we also work closely with the Space Environment Impacts Expert Group, quite a name, a group of academics from UK universities and research councils who support us to ensure the latest science is being fed into our assessments and our policy development. Internationally, not on this diagram, ESA, our key partner, and so are our colleagues in the USA, both in terms of forecasting and considering how we manage and communicate about this risk. And that's a really key issue I want to land. So Sai alluded to this in his presentation, and I'm going to go into slightly more detail. But the strategy is underpinned by 3 pillars: assess, prepare, respond, and recover. So the first pillar, assess, covers, as you might imagine, how we can better assess and understand the risk. It's about enhancing our understanding and our ability to forecast severe space weather, and there's 3 key commitments. The first is primarily achieved through the UK's contribution to the European Space Agency's L5 Vigil mission. I can't stress how important that mission is to us. The mission, I'm not a scientist, just before I start this, the mission will allow us to see a side-on view of the sun and the earth, providing further warning of oncoming solar storm events. This will provide the electricity industry with hopefully more notice of approaching solar flares and coronal mass ejections. Commitment 2 focuses on delivering the £20 million programme of research as part of the summer programme. I'll cover that in more detail shortly. This will enhance the Met Office's forecasting capability and ultimately provide us with more accurate and advanced warning of oncoming solar storms, and thus hopefully more time for government and industry to take the necessary action. And that's the key thing. It's not enough just to have accurate forecasting. It needs to get to those who are going to be able to act upon it, beyond government, but into the private sector who operate and own most of our critical infrastructure. And the third commitment under Pillar 1 is based on enhancing our understanding of the impacts of a severe space weather event. Government departments are working closely with their sectors to identify and understand impacts of a severe space weather event on their infrastructure and the ability to provide ongoing essential services. For the electricity sector, this is about developing a clear assessment of the effects of severe space weather on critical energy assets. Met Office have helped industry develop their knowledge of severe space weather through the provision of educational material, attendance at industry forums, and other specific engagement. The National Grid Electricity System Operator are also taking forward innovation projects to update industry understanding of impacts and asset vulnerabilities. The second pillar, prepare. So the enhanced understanding that we will develop through the first pillar will enable us to prioritize preparedness activity, the focus of this pillar. There are two key commitments here. The first is about critical sectors taking responsibility for implementing mitigations based on this enhanced understanding. And this goes back to my previous point. It is not enough to be able to just forecast the event or to understand space weather or even accept that it's a risk we should look. Making sure those who can take action to prevent or minimize those mitigations or respond more quickly is a key part of this. This will include updating technological systems, response plans, and incorporating space weather forecasting into their business procedures. Ideally, I would like to get to a position for those sectors where it's relevant that a space weather forecast is as normalized as a weather forecast is into business planning. From the electricity sector's perspective, we've seen excellent progress. In 2013, National Grid undertook a detailed impact assessment of how a severe space weather event would affect the nation's power infrastructure, and this was partly reflected in the RAE report. As a result of that, National Grid put robust operational plans in place to manage the impact of severe events. We've heard today from Matthew from ESA that they are planning to further review and update this work to reflect the new structures of the energy system, and we will need to do so again in the future. We should see this as a cycle of the process. It's not a tick box exercise. Given the cross-compounding nature of severe space weather impacts, other organizations in the energy system, distribution network operators in particular, are also working on updating their own plans. This is a strong example, from my perspective, of how a critical sector is working to become more resilient. The second commitment is for UK government departments to develop and test their own sector response plans. These response plans will set out clear procedures to follow in the event of a severe space weather event that will hopefully minimize and facilitate recovery from its impacts. Government has a clear role in protecting our citizens from essential service disruption, but we still need to work with our industries who operate them, and having that joint parallel approach to response plans is really key to the success of that work. And as a result, there will be regular exercising and improving of response plans through a lessons learned process, with the first major exercise planned for early 2024, providing an opportunity to test the electricity sector's updated response plans during this time. And I think that's really key. Normally, I'm a proponent of risk agnostic planning. Your plan should be able to respond to almost any risk without it being specific. But space weather is unique. It is also extremely complicated. Of all the many complex risks I work on, it's the one that gets the most eyebrows raised, the most, am I joking? What is that? And so we need to normalize that language, and that requires specific planning, specific lexicons to support decision makers. Finally, the third pillar, respond and recover. So for me, resilience is not just about stopping bad things happening, but it's about being able to respond to them, to recover from those disruptions as quickly, as effectively as possible. And sometimes that might be the most cost-effective way of managing a risk. Here it is clear that international cooperation is key to managing a response on a global level. Within this, there are three international priorities that the strategy identifies. Firstly, the standardization of data, and some of the questions earlier about the accessibility of data, but making sure we're all looking at the same data, we're all able to start from the same point, even if our analysis becomes different. This will help our respective forecasting agencies interpret the data they need to produce the timely and accurate advice that is so vital in responding to this risk. And also about being clear about where we don't know, where the analysis cannot take us, where the uncertainty is. It's not just that we need as much information as accurate as possible, but it's about understanding where Met Office, in the UK's case, but other partners cannot provide that data so that we can take risk-based decisions. Secondly, the rapid sharing of data. National Grid, I think, asked for 24 hours advance notice of a G5. I don't think SAI can yet provide that. I would like a week's notice, preferably. So understanding how quickly we can share that rapid data. If we've only got 30 minutes, who needs to know? How do we get it to them so they understand it, both domestically and internationally? The last 4 years, COVID, the illegal war in Ukraine, have all shown us that we have a global energy system, a global energy market. A weakness for one of our allies or partners will affect all of us. For the electricity sector, MOSWAP being able to provide more robust forecasts, alerts and warnings based on a greater body of valuable data being ready and available will allow coordinated messaging and contribute to consistent management of communications of impacts across the energy system. As Matt alluded to, sometimes response decisions can cost money or can damage the system in other ways, can reduce our resilience. So understanding from the best available data how to take those risk decisions is really key. And finally, conducting international exercises. We want to build from UK domestic exercises focused on one sector to multi-sector international exercises that will better simulate an event and ensure that cross-border mitigations are put in place. And those who've heard me talk before will know my biggest concern here is on international communications. If the UK government says, this is happening, don't worry, it's not the end of the world, and our partners in the US say, this is happening, everyone hide in your bunker, that's going to get out. We need to be able to explain why our messaging is different. For any US in the audience, I recognize you don't say that, but the point is around the messaging. The consistency and understanding why we have a difference in that message is really important. This will allow us to build our response plans from sector specific to national plans to international plans so that we are cooperating and coordinating as we move forward. So the SWIMMER project, Space Weather Innovation, Measurement and Modelling and Risk, another catchy title, is part of the first pillar in the strategy at PRESS. SWIMMER is jointly funded by the Science and Technology Facilities Council and the Natural Environment Research Council and aims to deliver an ongoing legacy of new space weather models and data producing instruments to enhance the UK's capabilities for space weather monitoring and prediction. This will go towards augmenting the forecasts and services offered by MOSWOC in the first instance. There are 11 SWIMMER programs allocated as part of the 20 million program budget, but the 5 highlighted projects are probably the most critical ones to the energy sector. So S2 focused on upgrading the CHIP IR neutron testing facility at the Rutherford Appleton Laboratory, and then most critically perhaps advertising this facility more widely. The electricity sector can use this to better understand the impacts of ground level effects on electricity switches and relays. S4 aims to supply the Met Office with a suite of solar wind models to improve their forecasting capabilities. This project is relevant across all impacted sectors, not just energy, as one of the limitations of the forecasting coronal mass injections is the orientation. S5 is an objective around designing, constructing and deploying a network of ground-based UK neutron monitors to the Met Office. The electricity industry, the data could be used to assess the level of risk to transportation electronics from ground level events. S6 focuses on producing an updated space weather impact study. This is updating the 2013 Royal Academy of Engineering impact study and is being led by RIA Group. The electricity sector is one of the key areas that we focused on in the new report, and there will be key partners in participating in the workshops planned as part of the feedback process. It is striking to me when I'm engaging internationally how often the RAE report is held up as an example of best practice, taking extremely technical data and translating it into an accessible format for a non-expert audience. And I'm keen that the updated report reflects that expertise. And then finally, N4 aims to produce a model and tools for geomagnetically induced current forecasting. This project is arguably the most relevant to the energy sector. The GICs represent the main risk to our national grid. The ground conductivity model can be used by network operators, distribution and transmission to assess which of their assets are at most risk and allow us to target our mitigation strategies. So I have another slide. You'd have lost the rest of my papers. Good, so I'm now going to make it up. So preparedness strategy progress. So the Met Office has taken significant steps through the SWIMMER programme, as I've just set out, to explore further research and look at opportunities for improving the data and the technologies available to us. In particular, looking at communications of that data, of those forecasts to the community, whether they be energy sector or more broadly, has been a key part of that. I am particularly keen that we have an international standardization of space weather data with bilateral partners. This will lead us to making more consistent assessments and using more consistent language to describe the impacts. What I don't want to do is ensure we're all doing the same assessment, because then we will get the same answer. Diversity of assessment is important, but consistency is valuable too. Greater public awareness. As I said, space weather is still one of the areas where I get the most surprise about my involvement and our work in it. So understanding that, removing red top newspapers having bright green pictures of the sun and telling us the world is going to end, and getting a more realistic assessment into the public discourse is really important. And a cross-government communication strategy and hopefully international strategy. It's not just the energy sector. There are other departments working on this for their other critical sectors. I won't go into detail, but in particular around transport, particularly aviation, to understand the impacts on avionics and component testing for radiation levels is really key. The newly created Department for Science, Innovation and Technology is also working with the telecoms sector to understand the loss of GNSS services and what that means for new communications tools, particularly in 4G and 5G systems. The UK Health Security Agency is working with the Radiation Chemicals Environmental Hazards Group to develop specific advice. And there's nothing that scares people more than saying there's a radiation risk. So having clarity on exactly what that means is really key. And the UK Space Agency continues to work with DCIT to refine the impact assessment and looking at the impacts, particularly around old and new satellites that have been shown to have different levels of resilience. Then finally, we recently conducted an electricity sector tabletop exercise, looking to test whether we needed to renew our understanding of the impacts on the energy system. We have historically focused on the transmission networks to manage this, whereas this brought together distribution network operators and generators. And some key learning has already emerged from that, will inform our work over the next year. So it's really easy in the UK to say national grid and describe the whole energy system, whereas actually National Grid itself is multiple different organizations, but it is also not the whole of the energy system. And so increasing the awareness of the Met Office briefing notices, the forecasts and what these do and what they tell you has been really key. And it's clear that that understanding isn't consistent across the energy sector. So making sure they understand the tools and the capabilities available from Si and his team has been really key. Governance and planning. So individual response plans. So what we've seen is a lot of companies have a response plan for space weather. And on the first look, that's great to see it's part of their risk planning. On second look, it's less reassuring. And what you find is that plans have been created in isolation and silos. Actions and activities by one company will inadvertently negatively impact another, or assumptions have been made about what player will do. So bringing those plans together, bringing the expertise across the sector to understand the totality of that risk and response plan will be really key. And then research and testing. So it's clear that we don't understand yet all of the impacts on all of the components in the energy system. And I think that's come across in some of the presentations we've seen earlier. So supporting further research across the scientific community where we can to understand the space weather effects on equipment malfunctioning and what this will mean for the energy sector is particularly key. Neutron beam testing is a particular area of focus where we want to understand the impacts. And then Matt said it and others have done it, but the energy system is changing. The energy system from 2013, as I've said, is very different from that now. It will be very different in 2030 and even more different in 2050. Some of those aspects will increase our resilience to this risk and others, and some will decrease it. We need to understand the totality of that and ensure that resilience to space weather is built in from the ground up as we move forward as a sector, as a government, and as a nation. And I think that genuinely is it for that one. Yes, thank you.
Thank you. We'll take a break.
Hi, so I'm attending Met Office. So I've got one question for you on kind of the big picture of kind of the improving our modeling capabilities, which is that in space weather, unlike terrestrial weather, we're very dependent on models from the academic community. And SWIM has been fantastic at pulling in some of these things and creating a space where like we can have academic goals that are aligned with trying to do the boring implementation bit, but on a normal basis, you know, for academia, you're trying to do paradigm changing stuff. You're not trying to do incremental improvements, and incremental improvements, a few percent year on year is what has got terrestrial weather to what they call the quiet revolution of terrestrial weather forecasting, and these kind of this virtuous cycle that just it's a ratchet that gets better year on year. And so the question for you from government with the money is, can we create a way to be able to get, if nothing more, just a trickle, but ideally more than a trickle, but for being able to make sure that we can get some academic stuff where they can do some of this boring stuff that the research councils tend not to want, tend not to be favoring so much?
Yeah, so I think, so firstly, when you say government has the money, we don't have a lot, just to be clear. I think space weather is a really good example of how we have tried to do that. And I think Swimmer is having an effect, and our day-to-day engagement with the scientific expert group is also a really good example of that. And bringing the government expectation and our objectives together with a more realistic understanding from the science community about what we can fund and what that can deliver. So I think that model is having an effect. Swimmer ends next year, as you know, and we are looking at how we then put money into the most fruitful parts of that to continue and build upon those as part of it. My experience is that normalizing scientific input into high impact risk planning is definitely on the cusp of being there. There is not a risk meeting I go to now where we don't discuss, have we got the right scientific expertise in the room? I think what we need to do more of is build our common understanding of working. And you often see in meetings that bring together government policy officials with scientific experts, we're almost talking a different language. The first time I met with the space weather steering group, the first question the scientists asked me is, how much resource are you putting into this? And it's like, well, you've got the next hour of my time, and that's probably it for this month. And so working out how we can work together to collaborate, how we can share our resources is key. And I think this is a really good example of that. And we can take the success of programs like Swimmer, not just to further space weather forecasting and capabilities, but also into other risk environments. And I think as the COVID inquiry continues, one of the key aspects of that will be, or one of the key learning aspects of that, I suspect, is going to be, we need more, better, regular integration of scientific input into crisis management, into risk planning. And I think that will be what we start to see coming forward.
Hello, Andrew Larkins from Sygensis. I was delighted that you highlighted quite how different the electricity grid is going to be in the 2030s compared to what it's been historically. We're going to be in a situation where we might have 10 million EVs connected to smart charging control systems as part of the electricity grid balancing mechanism. Within that, what that does introduce is quite a cross-coupling of systems between the communication networks and the electricity grid. You mentioned within the presentation, for example, the risks associated with 4 and 5G communication systems. That has feedback into the electricity grid itself. Is that something that you see being studied a great deal at the moment?
Yeah, so I think the interdependent nature of critical sectors is getting more attention than ever before. The UK conducted the largest crisis response exercise ever back in March this year, which focused on a widespread electricity disruption, and in particular on its secondary impacts onto the communication system and other critical services. So I think there's definitely greater understanding than ever before into that. And I think, the real debate is, should we focus our time and effort and resource now on the new systems, whether it be comms or electricity or anything else? And if so, what risk exposure do we leave on the old systems? And ultimately, you can have as much resilience as you're willing to pay for. And we need to work out. And as I said at the beginning, resilience isn't just hardening, it's also response. And we need to work out exactly where the balance is. But I think collectively across government, and certainly in the interactions I've had with the private sector, there's widespread acceptance that resilience will have to be built in at the ground from the new systems. And that hasn't happened before. I think that's the game changer. It alludes to the previous question, I think, around how we bring science in from day one into those developing systems. to improve resilience. So yeah, I think it's, in short, a real focus now, and one that's likely to continue.
Thank you for the questions. So we actually have we're going to have to wrap up there. So thank you again. So yeah, first of all, thank you for all of your talks. It was very interesting. I think we covered a large area, a large breadth of knowledge, and yeah, covered basically all the bases of space weather impacts on the electricity sector. So I'll kick us off with one kind of general question to bring us back to the room, and then we can throw it out to the audience and we can fire away questions. We've got about 40 minutes. I have some more prepared questions if we need, but I think you can come up with enough. Yeah, to get us started, I want to bring it down to reality, well, with a hypothetical, so not really reality. But my concern is that we often, well, we have 20 years of no major space weather events. And I want to give people a flavour of what a major space weather event and impact on the electricity sector would look like. So if there was a major space weather event that happened tomorrow, or started tomorrow, and maybe took over a few days to weeks, what would that look like, both from a space weather kind of hazard characterization, but also from an impact on the grid and response from industry and government? So maybe Simon could start with, and we'll work our way down.
Go with so what would a severe space weather scenario look like? Well, as I mentioned in my presentation, the reasonable worst case scenario that we use to underpin the national risk assessment in the UK talks about an event broadly of the scale of Carrington, appreciating everything that's been said about our lack of being able to measure Carrington particularly effectively, or being able to measure anything effectively in any way apart from magnetism associated with it and the magnetic effect. So we're making estimates of, broadly a 1 in 100 year geomagnetic storm, maximum extent, radiation storm, solar flares, but we're not expecting just one of each. We're expecting a series of those. So we're expecting to see a large active region rotating onto the Earth-facing solar disk, and taking in the order of 2 weeks effectively to cross the disk. I suspect if we did see such a large event, we wouldn't be just looking at one single area of sunspots. We're probably looking at 2 or possibly even more areas of sunspots that may be generating different levels of activity over that 2-week period. So I'd expect to see a series of solar flares, geomagnetic storms associated with coronal mass ejections, and radiation storms. But they won't always be at the same time, and they won't always be geo-effective. So some of those early, we might see some flares as that area rotates around onto the Earth-facing disk, and the flares, of course, would be Earth-effective. But radiation storms from that particular region probably wouldn't, or wouldn't be expected to have a massive effect. As the region rotated around the Earth to be more Earth-facing, then we would expect coronal mass ejections that might be lifting off to be more Earth-directed. And so the first few days may well be affected more by flares. A few days into it, we may be more affected by coronal mass ejections. And towards the latter part, as we get the magnetic connection with the Earth and it rotates towards the far limb of the sun, we might well see more in the way of impacted radiation storms. So there will be some changes, I think, over that period. Could be a whole range of impacts. So we'd expect there to be G5 storms within that, of course, but there might be some much lower level storms as well. There'll be a series of coronal mass ejections, and the fact that we might see some slow moving coronal mass ejections might just be clearing the way and reducing the friction, if you like, for faster corona mass ejections to follow that, which of course would be more impacted. So it's a complicated picture, isn't it? We all know that, I think. It's a complicated picture, but we'll be looking at something like a 2-week period of activity. We'll be seeing lots of individual phenomena occurring within that period, some of which will be larger than others. Probably one of the biggest dangers is seeing a moderate speed CME followed by a really large CME. Once, as I say, once the space has been cleared for it to actually move really quickly and impact on Earth in something like 14 or 15 hours. I mean, clearly these sort of effects and the large CMEs, again, as has been talked about, they'll energize the atmospheric electrojets. They'll lead to the potential difference and will end up with geomagnetically induced currents. How those feed into the grid and the impacts that will be experienced, and whether there are impacts, again, as much as it's much more than just the grid. It's about generation. It's about distribution networks. So perhaps so.
Yeah. So we do monitor your alerts and warnings and notifications, and given that you've identified an active region and you think there's a risk of severe storms, particularly geomagnetic storms. Working closely with the Met Office, with MOSWOC, we would then go into our first level. So we have 3 notification points that we have our own notifications that we issue to industry, and mitigations or actions that we take according to those notifications. So we would be, once we have some confidence in the level of strength of storm, we'd be looking to stop outages from going ahead, because on a normal day-to-day basis, we're taking bits of equipment out on the network, and got more transformers in service at a node that is at more risk, at higher risk. That reduces the GIC that would be through a single transformer. So having one out of service, one in service, you're going to put that other transformer at increased risk. So that's why we're taking actions to return assets to service. We'd also be doing a similar sort of thing, but for reactive compensation equipment. That's basically equipment that is used to manage the voltages on the network. Because as we talked about earlier, if you've got a GIC running through transformers, you get an absorption of reactive power, which reduces the voltages on the network. It could cause demand loss if that voltage fluctuation is large enough. So we want to try and get those bits of equipment in service where we can. If the storm's going to last for quite a long time, then we've got, we'd make sure those bits of equipment were in service to cover the whole period, clearly. Loss of generation, so generation transformers also could be vulnerable to GIC and damage. So the potential for the loss of a generator, which we would be able to manage by either instructing interconnectors to provide more power, or to run additional levels of response and reserve. So we always cover for the fact that a generator could be lost at any time for just regular reasons, but we would add on extra levels of reserve to make sure we can cover that, knowing that there's this increased risk from GIC. Yeah.
Perhaps Mark, about the government response.
Yeah, well, actually, the government response will be what it is. COBRA will form. We will oversee the situation, wait for the information, but actually, I don't think it's the most important thing, because I think a lot of that will happen behind the scenes directly with MOSWOC and National Grid, and and others. I mean, the most important thing I would draw out here is, and the answer shows the complexity of this. Most of the public wouldn't understand what we've just said, and will want to know, what does this mean for them on the ground? You know, loss of a generator doesn't mean anything to the public unless you lose security of supply, and National Grid have that well in hand. And so I think the electricity disruptions relating to space weather aren't going to be the biggest problem. It's not the lack of electricity. Most of the time, we know how to manage lack of electricity. And for most people, it is just simply a case of flipping the fuse back on a few hours afterwards. Now, this will happen repeatedly, potentially, there, and at the ends and tails of the network, we'll see a problem. I think the biggest issue associated with lack of electricity for the wider public are the secondary impacts. Major industrial plant being disrupted. Once it loses power for more than 30 minutes, it'll take a week to come back online. What does that mean for just-in-time supply chains? Communications, you know, I can cope without my light switch on. I'm less happy if my mobile phone isn't working properly. How much reliance do we have on GNSS in everyday lives that we don't know? So the example everyone goes to is ambulances. The ambulances will struggle, they'll have maps, but no one knows how to read a map. More people know how to read a map than we allow, but it's more of our day-to-day activities. And I think when we think about societal resilience to electricity disruptions, thinking about those secondary impacts is much more important. If my mobile phone doesn't work properly, if my app to check if the tube is running doesn't work properly, if my banking app doesn't work properly because of some dependence that I didn't know, because as a member of the public, I didn't need to know and wasn't particularly interested most of the time, what risks does that create for me? If I can't get cash out, do I start to worry? And does that create a bigger problem? And so, you know, for me, that is the biggest risk associated with space weather. I'm never worried about whether National Grid has this in hand. You know, we've spent many years working together. I know the behind the scenes stuff, and that's what government will be focusing on at first, is National Grid doing the right thing? COBRA will be set up, ministers will be informed. We're trying to work out how to explain space weather to them in a one slide approach, bragging Si or one of his team to me to make a nice picture. The technical stuff will happen, and will happen well, I think. The biggest challenge is the public interface with those impacts. And that can create a lot of reactions that we don't foresee. And it's not just space weather scientists who need to be involved in this discussion, it's behavioral scientists who need to be involved in this discussion to think about how we react, because that's what drives our response planning. And if I can't get cash, if I can't get toilet paper because the supply chain got disrupted because the lorries didn't have a map, couldn't use GNSS to get around, what does that begin to create? What are my knock-on impacts? Especially if, as Si says, this is happening over a 2-week period. If it keeps happening, how does the government reassure the public that we have this in hand? Because the first thing you do in reassurance is tell them it's not going to happen again. If it happens again 6 hours later and keeps happening again 6 hours later, your credibility is undermined. And because it's such a technical subject, how do you bring that expertise to the public in a way they will understand? And I think for me, and despite the fact that I'm responsible for electricity resilience for the government, that is the biggest risk. It's not the direct impact. I'm confident we can manage that. It's the indirect impact that we don't know. I remember years ago having discussions about, would train doors fail, shut or open? No one knew at the time. Now, well, that creates a big risk profile. Will everyone be locked in a train, or they jump onto the lines? Are the lines live? And that's true across all sectors of society. And the traditional critical sectors are critical to provide an essential service, but there are a lot more other services that we rely on now that we don't think about as critical up until the moment we don't have them. And I think, for me, that is the biggest uncertainty around this risk.
Thank you. Any questions from the audience? Daphne's got a hand up.
We have a lot of questions from online. I'll go with the first one that I spotted earlier for Matt and for Simon. And Matt, if you can be closer a little bit to the mic. So the question is, if there's 2 weeks of severe solar storms, would it be possible to repair any damage while they're going on, or would it mean 2 weeks of potential outages?
So if the storm was severe enough to damage transformers, then potentially we could have a loss of supply while we re-switched at those substations, which is basically get the supply from other places, because substations are quite flexible. You know, we can get links to other substations, not just on our network, but also on the distribution network. So in some cases, there'd be very short disruption that could be then re-switched. But in some cases where potentially, you have maybe a outage on a transformer that is in, it's in complete bits because it's being replaced or whatever, and then you lost another, because there's always redundancy at the sites, lost a transformer, then potentially it would take time to get that transformer replaced, either by sort of strategic spares that the transmission owners could arrange. Yeah, so that's the answer. So I think potentially, we in our analysis, we're looking at, in the worst case scenario, you could lose between around 13 transformers on the network, but that could mean that you lost maybe 1 or 2 nodes with the demand disconnected for a few days while those spare equipment was brought in.
Take questions from the audience. Okay, I'll choose someone that hasn't asked one yet. Yeah.
Hi, my name is Elliot James. I'm from the Rail Safety and Standards Board. We work in the Futures Lab, so we look at emerging risks, resilience, adaptation, future vulnerabilities to railway infrastructure in the UK. So this touches a little bit on the comment that you made about that public interface with second and third order impacts of an extreme space weather event. And something that you mentioned in your final presentation as well, which is about increasing public awareness of and preparedness for such an event. So related to this, I saw an article that was published by NASA recently, and it was talking about the probability of something that they termed an internet apocalypse around 2024, 2025, of course, related to an extreme space weather event being on set. And I was having this conversation with my girlfriend and her 17-year-old brother, and his response to it was, "Oh my God, the world's going to end." And he said it with a bit of a smile on his face, which I found quite concerning. So my question kind of arising from this is that, with this in mind, what approaches are currently being taken to increase public awareness of this risk? And how do you think this approach to increasing public awareness and preparedness could be achieved to avoid communications that generate fear?
Start?
Go ahead, Simon.
Okay. So from a Met Office standpoint, we have responsibilities which are laid out in the space weather preparedness strategy to increase public awareness. We do what we can, but obviously we are resource constrained on that. But so as regards public outreach, we have over recent months put together a series of space weather explainers, which are very basic, nice cartoon type of animations. There are a number of those out on YouTube. We use our social media channels in the Met Office to advertise space weather, to talk about space weather when we can. I say advertise events such as this even, but so we engage in those sorts of activities. And then, of course, there are the engagement activities we take with schools and people in education. Personally, I've been out to the National Space Centre in Leicester and given presentations to school and college children, young people, around space weather, to try and, well, advertise the space industry and the interest I have in that in general, but also increase awareness and engagement with space weather activities. So we do what we can. We are in the process of pulling together a fuller communications plan, cross-government communications plan for space weather. And within that, we plan to set out a number of campaign opportunities, which we would hope to take forward over a period of time. But as I say, we are also resource constrained on this. We only have a small number of people we can set to it. So we do what we can, and it's a clear commitment, and it's something we take very seriously, because there clearly are some risks around public behaviours if people are taken on the back foot and they feel they're not getting the right sort of communication. And we're also acutely aware of the sort of things that Mark was highlighting previously about appropriate, measured and consistent communication. Clearly, we want to avoid the sensationalist sort of, the sun's falling apart, the world's coming to an end type of stuff, and put together a measured message. And we use things like the Press Association. We put out articles to the press through the Press Association in the UK, again to try and help manage those messages. And I know that Alexi's probably going to say a very similar set of things around ESA activities.
Yeah, perhaps I can comment and speak to that point as well.
Yeah.
Thanks. Yes, I mean, the communication, of course, is something that the ESA also takes very seriously. And so within the resources we have available, so we take a number of different actions in the area of communication. For the wider public, we also use social media. We have a dedicated ESA Space Weather social media channel that we use to communicate information about general interest about space weather and about activities that are happening within the service network and wider activities we're engaged with. We also work directly with universities. We've just established a collaboration with the ESA Education Office to develop a training course for master's level students. We had the first course this year and are planning now for the next spring. But also one thing we focus on intensively with the service network teams, and actually we're planning to run a campaign next week. So it's very timely actually for us. Is this the point about coordinated communication? So we recognize that we have a large number of teams participating in the service network activities we're involved in, 50 plus teams spread across the European region. And in the case of major events would take place, then we would aim to have all the teams participating in the network communicating a consistent message rather than each group giving a separate summary of the activities that are taking place. So we have a protocol that's being developed also with the collaboration of our colleagues at the Met Office, which we test and exercise regularly with the teams, and a process whereby we have a set of triggers. If one of these space weather triggers is met, then this protocol is activated and we start issuing regular and as needed bulletins on the conditions that we would then, in a real scenario, be communicating outwards with the collaboration of our communications office in ESA to our different stakeholders. So really focusing on making sure the information that comes out to the public is accurate so that we can help address those sorts of.
Take another question from the audience. No, you. Oh,
thank you.
It's okay. We'll go to you after. It's okay.
Very quick. It's really a pity you haven't got anyone from the UK universities talking at this event. Really, because there's a fair bit of work being done. But my question is to report Carrington. The report given by ISPRA and the Met Office and NOAA produced a report in 2016 saying there's a 10% chance in the next 10 years that there'll be a Carrington type event. So in your opinion as a panel, what effect would that have? Because that's quite a high chance would have on the infrastructure that you know of. What effect would it be on the infrastructure if there was a Carrington type event in the next 5 years?
So, Met Office helped develop the 1 in 100 year event scenario, and that's what we base our response plan on, which is Carrington strength effect, I believe.
Yes, yes, broadly speaking.
So that's what we operate to as a reasonable worst case. And we've got our mitigation plans in place to trigger those mitigation plans when we think we're in that scenario. And you know, the effect on the system is, as we've said before, which is the potential for damage to 10 to 20 transformers, and potentially a loss of supply at 1 or 2 demand points on the, and it likely to be at the points on the country where are most vulnerable, which tends to be around the edge and around at the coast. So that's what we think the impact would be.
Do you still have a question? Yeah, so maybe in the middle.
To what extent can you use the geological records to determine the magnitude of past space weather events, so ice cores and that sort of data?
Not really at all.
Not at all.
No, it's one of the issues with geomagnetic activity is it's not really recorded. There are some hints you can get about things like ground level enhancements or solar proton events from ice cores, but they really don't tell you about the geomagnetic things. You can go back into records of, you know, there's writings from like the 13th century of aurora being seen in unusual places, but that's normally, you have to really understand what you're reading because it's kind of, it's at the time, so it's, you know, the sky turned red on this night and we can infer that that was a geomagnetic storm, but that's kind of all we've got. And that's one of the problems with defining this Carrington level or 1 in 100-year event is we only really have, say, 200 years of measurements, and actually only since the 80s have they been digital. So they're like the records we've got now. Beyond that, they're all very analog and very difficult to interpret. Efforts are made, but it means we don't have a continuous record for lots of time. We can use geomagnetic indices, but again, they only go back to, I think 1957 is the longest geomagnetic indices, but they're on a much, they don't tell you a huge amount GIC because they're on a 3-hour time scale and they're about a range rather than rapid variations.
And to add to that, it makes it extremely difficult, or rather, it makes any estimate of the intensity of a 100-year of storm or beyond extremely high uncertainty. And then I don't think the nuclear industry has really come up yet today, but in the nuclear industry, there's interest in events out to 10,000-year events, which is a magnitude that's beyond anything that we have data for. So uncertainty bounds are huge. We can use some geological data for the ground level enhancements, which can give you an estimate of the fluence or the integrated flux during a extreme ground level enhancements. But again, large uncertainties upon uncertainties, and you end up getting really quite large events. We'll take another question from the room. Alex.
Hi, Alex Carroll, EDF. I was interested earlier to see that you know there's an explosion of data collection capabilities. You know, the magnetotelluric sense network that's being developed, satellites and all those things. And it occurred to me that you know nobody's talked today yet about the duration of a specific GIC wave, and then you know there are estimates out there that this could be somewhere from 2 to 30 minutes, perhaps could be longer. There's not really a clear answer to that. Do you think? Does the panel think that you know with this this new data collection capability coming online that we will in time develop a response to that question? How long is a specific GIC likely to last during that period where we are at higher risk? But it's not as Simon said, it's a period of potentially 2 weeks where you've got several events. The question then is, well, how long is each event?
Yeah, it's a good question. So we can look at previous storms and you can see that, as you say, during a single geomagnetic storm, you're not seeing, 100 amps of GIC for the whole thing. You're seeing peaks and troughs. So you can get some sense of it. I was actually talking to someone in the break about we need to do a bit more work on understanding that. But within any geomagnetic storm, you have what we call substorms. So you get these it comes back and then it dies off again and then it comes back. And it's really hard. And it's something we've talked about before, is how do you say, okay, that's it, it's over? Because that can be just as important to know as that there's something going on. People go, oh, well, we've not seen anything for an hour or so, we'll turn everything back on, or whatever the case may be. But yeah, I'm not sure what the answer is. And as I said, if you've got a really big series of sunspots that are blasting off lots of different CMEs that might interact or might not, then you might say, okay, this storm's over, but then 12 hours later the next one starts, and that can get really confusing as well if you've told everyone that the storm was finished, but then something else hits us and it all starts again. It's
do you think that with the new data collection capabilities that are coming along, we will develop an improved understanding as and when we get events actually to measure? Appreciate that we would like them not to be extreme at that point, so we can be moderately strong, not strong enough to measure.
Yeah, we can definitely learn a lot more by having more measurements than we do. And even the measurements that we've got now, like there's so many more observatories now than there were for the last big events. But as you say, until we start getting some bigger events, it's kind of hard to know. I think the biggest issue is actually the monitors in space. We're very reliant on one or two data points. And if we lose those data points, we're kind of blind. And that might be the bigger issue in terms of instrumentation capability. So.
Take a question from online, Daphne.
Have we quantified the financial loss of a Carrington-style event happening today?
Or pass?
There are papers. I was involved in a paper a few years ago about the socioeconomic risk, and the risk massively varies depending on how good your forecasting capability is. So like we said, if you've got a satellite at L5, which we will hopefully have in a few years, and the satellite at L1 and the 24/7 operations, you can hopefully reduce the potential for loss. But I cannot remember what any of the numbers are, so I'm not going to throw random numbers out. But there are papers that have tried to quantify it. But whether they capture everything, who knows?
Yeah, and I think Mark's mentioning of the tendrils of dependencies could potentially make any number quite uncertain, and perhaps underestimate a particularly severe event that took out things that had tendrils of dependencies which weren't expected or weren't known about.
I think that's clear. It's a very difficult, very challenging thing to do. I mean, one number I can perhaps quote comes back to the 2016 cost-benefit analysis we carried out for the space safety program, where the study team estimated that one major event of that class could cost up to, in 2016 financial conditions, and up to 15 billion euros for one event. And actually one of the largest contributors to that was the impact on the energy sector indeed. And so one thing we're just about to start now as well going forward is a revisiting of this study. So a new socioeconomic impact assessment for the full European region, which will again revisit these numbers and give us an updated assessment of what the potential impacts could be financially.
Take a question from the room. Question over there.
Sorry, I just wanted to comment.
Could you wait for the mic? Thank you.
So I just wanted to add something maybe to that point. I think in 2012 there was quite a severe event that actually missed the Earth. It hit stereo A, and it's very difficult to talk about what a Carrington event looked like, but people talk about that being Carrington scale. And I think it was after that there was a National Academy of Sciences study in the US that I'm wary about throwing numbers around. This is something that I've just checked on my phone before I said it. They said if that hit the Earth in the first year, the economic damage would be up to 2 trillion. So I don't know, please go away and look at it and don't take my word for it. But yeah, well, yeah, it's there.
Mike.
Just a couple of one from Mark. The problem with the transformers is magnetic saturation. I mean, if you unload the transformers or deload them to a certain extent, then they don't go into saturation, so there won't be any damage. I mean, that's certainly something from a generation point of view. Synchronous generation is, you want to pull back on real power that maintains your ability to produce VARs, but effectively means the transformers don't go into saturation, and you can do something similar on the transmission system, even if you have to actually do rolling power cuts to maintain that level of unloading to ensure that you don't have damage, and then you don't have to replace things. Or
yeah, I think that the issue could be that if you're taking transformers off, you're putting the transformers that are in service at increased risk.
yeah, no, I'm not saying take them off. I'm saying keep them all on, but you effectively unload them by reducing demand or reducing generation.
Yeah, there's something that's been talked about for generators where they do tend to operate closer to the capability of the transformer. So that's something that has been discussed with industry, is currently still being discussed with industry about whether, commercially it might be sensible for them to offload or deload or reduce the load of their transformer, the generation that they're producing to protect the transformers.
And
sorry, can I just comment on that though? I think you have to understand the totality of the risk. So what we might save in some transformers that aren't damaged, the cost of rolling disconnections and rotor disconnection is significant, and we would likely have to have the government direct that happened, and it couldn't be done preemptively without our say so. And one of the big things we look at all the time is the impact on the rest of society from that, and we would need, as part of that assessment, to understand that the mitigation is better than the cause.
Yeah, I quite understand that. It is that trade-off between, okay, so I've damaged a load of transformers and it's going to take 6 months to return them to service. And there's a trade-off there. I mean, as far as from what you were saying earlier, you're talking about DSIT doing some work with the telecoms people as well as GNSS. Are they looking at the effect of GLE on the telecom systems themselves as well?
Yeah, no, that's part of their broader work.
It is.
We have an audience member chomping at the bit here.
Yeah, I'd just like to comment on the point made about deloading transformers. The issue is that deloading transformers doesn't impact the magnetic field within the transformer. The magnetic field is dependent on the applied voltage. The energization of the transformer is provided by the applied voltage rather than the load current on it. So actually deloading the transformer doesn't actually make it less sensitive to the GIC. The GIC produces a DC offset in the field within the transformer, which is forcing it into saturation. So the option to reduce the impact on the transformer is actually to reduce the voltage at the transformer that takes the magnetic field further away from saturation. But obviously that has wide impacts on the grid. As you lower voltage, you impact consumers and potentially impact generators as well.
In the interest of time, we've just come up to the end of our time, but I feel like there's a conversation to be had offline there. So Mike is returning that. But we'll leave that till offline. Thank you everyone for joining. Thank you first to the panelists. Some really fruitful discussion following some really good presentations. So thank you for joining us today and giving us your time. Thank you for the venue staff as well. I think the team that have helped with the audiovisual and with the catering is appreciated by everyone. And to the rest of the organisers, Daphne and Catherine, Katie, who's not here today, and Nick, who's just left. Yeah, so maybe a round of applause for everyone that's been involved. Thank you.